Okay, good morning all. Can you hear me all right and see the screen?
Good morning,
Yeah,
Professor.
good
Yes, we
morning.
can.
Okay, very good. For some reason, more people should join. I don't know if it's because of the winter and people are getting up late. But anyway, I guess we should get started and let them join in the process. So we are at week 4. And today, the main new content that you will see is on one of the foundational aspects of what is known as Gen AI, generative AI. Um, Generative AI, as such, has evolved over the past, say, 7, 8 years, and has become a very predominant tool for various analytic tasks, uh, mostly related to images and vision, but also it has played a role in uh, generating data whenever, for example, there is not enough uh, ways to gather data, right? So, and starting from the basic concepts of Gen AI, uh, starting from what is known as PCA, I will try to connect one of the first generative AI neural models. PCA, as such, you might have already seen or heard about this in the previous modules, but I will give an introduction to PCA. Will not go into much of the details, but then once we know what PCA is, we will see what is the transition that one has to make from going from PCA to something known as an autoencoder. And autoencoder further uh, was uh, with a slight modification, introducing a Bayesian philosophy or a variational philosophy. That a model that was created was the variational autoencoder. It is a variant. Variational doesn't mean variant. It has a mathematical meaning to it, which is mostly the Bayesian approach of autoencoders. And then we will move towards what is known as generative adversarial network, which all of these models that I mentioned, autoencoder, variational autoencoder, and generative autoencoders, uh, all these are ideas uh, that lead to generating data samples. Generating data samples, for example, I give you data from a certain distribution, and you would like to learn what is the underlying distribution, and then now you start generating samples from that distribution. Now, for example, if the data that you would like to generate is from a class of images of animals taken in a forest. Now, you would like to learn what is the underlying data and then start generating similar images, right? So that is the basic idea behind generative AI to generate realistic samples. Now, this has applications, for example, in AR, VR, where you would like to do scene rendering or to do imputation of scenes that are not completely captured, right? So you would like to, for example, extrapolate what the scene would look like in a more realistic way. Uh, Recently, so GAN the topics that I will cover today will basically form the foundations of what is behind generative AI, what are the underlying principles, and what is the basic idea. Further, if someone is interested in this particular aspect of generative AI, what is the most recent development, which of course will not be covering because of the time constraint that we have, is something known as diffusion models. So diffusion models also have the underlying philosophy of generating samples, but they follow a slightly different philosophy than what we will cover today. But the idea again is to start generating samples from a certain distribution that we learn that would mimic the underlying data distribution. So keep in mind that when we are generating samples, it doesn't make it's not of much use if you start generating samples from the training data itself, right? So it's not about repeating the same samples, but you should, for example, like I've seen image of a tiger, then there's no point reproducing the same tiger, right? So you would like to somehow see that, okay, there is a tiger and there is, say, a polar bear, and now I'd like to generate, say, a white tiger. So this is like uh, 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 um, uh, a thinking out loud example, but that is more or less what we would like to do with generative AI. So generate more samples. We'll see what are the applications of these generative AIs, for example, to do anomaly detection as we progress towards the end of the course. I mean, towards the end of today's lecture. So what we will do is recall that in the previous lecture, we were dealing with sequence models. Uh, uh, we will continue where we left in the last week, the discussion on RNNs, particularly developing what is deep RNN models, and then two important variants of RNNs, that is LSTM and GRU. So we will spend most of the first half of today's lecture towards uh, the continuation of the sequence models. And then, so the new concepts would be LSTM and GRU, but deep RNN is kind of the straightforward combination of what we have already seen in the last class. Then, as I mentioned, we will see two generative models. One is autoencoder and the generative adversarial networks. So I'll start with PCA. For people who are aware of PCA, it will be kind of a repetition, but if not, you will just get like a 2-3 slide introduction of where PCA is useful, etc. But this is mind that PCA is not a neural network or a deep learning based approach. Uh, so we'll see how to now make this non-neural network based approach a neural network based approach, and relate that to what is known as autoencoders, and then variational autoencoders and generative adversarial networks. So this is the plan for today. Let's see how much we can how much ground we can cover. And as usual, if at some point, like, okay, we will have to stop because we are running out of time, we will pick it up in the next lecture. So one important distinction from the 3 weeks that we have seen so far, predominantly we have been covering, or we have been only covering supervised learning models. Now, in generative models, there is no supervision as such. There is no labels. You only have data, right? So you only have data and you don't have class labels. And that means that we'll be focusing on unsupervised learning settings. So that is basically the distinction. I will elaborate what is unsupervised recall again when we get to that point. Okay, so that is basically the plan for today. Now, to again recollect the context, what we were discussing in the previous lecture is that I give you a sequence x0, x1, and so on till, say, xt. Now, having seen this sequence, the goal of, say, a one-step predictor would be basically to predict xt plus 1, give an estimate, having seen all this. Now, if you want to do this, what is the approach that you would like to follow? To understand how the sequence is evolving, what we would like to do is we would like to understand how the sequence is evolving over one time step, right? So what is the pattern that we can x1, x1 and x2, and so on? We would like to understand what is going on. And from that, we would like to predict, given x2, how does xt plus 1 look? Now, in doing so, what that necessarily means is you're not just looking at one sample behind, but somehow you'd like to incorporate all the historical data and understand what is going on. Now, in the last lecture, I was focusing on a one-step predictor. So this is called as a one-step predictor. You can also think of a k-step ahead predictor, which basically means that I have x0, x1, x2, and so on. And then I would like to predict, say, xt plus k. Okay, so I would like to predict something in the future, not just the immediate future, but say it could be, for example, not just the kth step ahead, but it could, for example, it could be xt plus 1 all the way up to xt plus k, right? So I would like to predict that entire sequence. Now, in case of text, all these x0s, x1s, x2s would be tokens, and these are vector representations of these words. And typically, if you have not seen the previous lecture RNNs, if we go back, what are the tools that people have been using? They would use something known as an autoregressive model or a moving average model or an ARMA model. So these are mathematical statistical techniques that people have been using where we force a model. For example, an autoregressive model could be, say, xt plus 1, that is the sample at time xt plus 1. It can be depending on the following. So it is, say, alpha times xt and beta times xt minus 1. So it depends on the previous two samples with some coefficients alpha and beta, and then you figure out what are these alphas and betas. Okay, so how do we do that? By fitting a loss. It could be in a supervised manner where you try to give the estimate as the following, right? So you would like to, so this is your model for your estimate, and you would like to optimize this loss, say a squared loss over all t's that is available with you, and this is your loss function, right? So 1 over t, and then you would try to figure out that this would be a function of alpha and beta, right? So this is one such simple way. Now, why should one consider only say a linear combination, right? So you could consider a nonlinear combination, or you could consider a rational response. So instead of taking like alpha time alpha, so only in the numerator, I can write this transfer function as a ratio or a rational, that is ARMA. I'll not go into the details of that, but traditionally those are the techniques that people have looked into for modeling of sequences. Now, the simple linear model has limited capabilities. Uh, Predominantly, the limitations are, I will get back to this. One is known as trend and seasonality. So any sequence model, I'll tell this now and then uh, uh, come back to this again if needed. So whenever we look at any data, for instance, it could be like sales data. Yeah. So uh, sales data for a company, for example, if we know, for instance, that the sales of a certain commodity is increasing every month. You are now predicting the sales, and we know somehow that the sales is increasing by 5% every month. Okay, that is the trend in the data. If we know that the stock prices are going up 1% every month, then that is kind of a trend in the data. Now, whenever we are learning this, we would not like to uh, uh, be biased because of the trend in the underlying data, and often what is done is that trend is kind of removed to capture the underlying patterns, dynamic patterns in the data. And to remove the trend, it's called detrending. Most of the ARMA or AR models whenever you would like to use that for prediction, one has to do detrending. It is like kind of feature engineering, putting in the AI context, but that detrending has to be done to use all these traditional models. But RNNs, because we are trying to fit a nonlinear model, nonlinear function of all the historical data, that detrending is not needed. Similarly, seasonality in a data would mean that there is some kind of a periodicity in data. For example, uh, say, for example, currently it is winter, and the typically, if you look at sales of winter clothing, right? So sweaters or jackets, that would basically increase around winter, right? So before and during winter. And again, during summer, nobody is gonna hopefully buy sweaters, unless, I mean, that would not be seasonal, right? So every season, okay, there is a behavior, the purchase behavior pattern there, and that is called a seasonality. And if uh, that is not removed in these traditional models, then typically the models that the prediction that these models would do, AR and ARMA, the traditional ones, they would be again overwhelmed or biased with these seasonalities. So one of the main advantages of using RNN or any nonlinear sequence models like RNNs would be that we don't have to worry about these things, and we just simply throw data, right? So just like how we were throwing images to CNNs, it is going to take care of all the required features. Uh, Depending on the labels, if it's like localizing a tumor in a histopathological sample, like related to healthcare, or it could be simply putting a bounding box on a natural image, right? So depending on what task it is, it's going to figure out what are the relevant features. So similarly, depending on the task at hand for RNNs, it is going to figure out, okay, should it remove trending, should it do detrending or seasonality? And it will not be an obvious detrending. It is going to be a nonlinear function that we will not even be able to make out. So this is one distinction that the RNNs basically provide. Okay. So anyway, so that was kind of the background about ARMA and why should one use these RNN models. But again, recollecting what we have been doing in the last lecture, that was one of the discussions that where we were pausing in the last lecture on ARMA and AR, but continuing the recap. The basic idea is that compared to a perceptron, the recurrent neuron gets two inputs. One is coming from the current feature, xt, feature at the current time, and then one something from the past. And the past is stored as a latent variable, right? So HT is a state information that is being propagated from one time to the other. XT keeps changing with time, HT keeps changing with time, but HT has a recursive relation. It depends on HT minus 1. Since HT minus 1 depends on XT minus 1, HT also has some information about uh, uh, um, uh, uh, XT minus 1. So now, if you look at this expression that I wrote versus what we had for the typical AR versus this, the idea is more or less similar, except that now I'm replacing alpha with some more parameters. So alpha becomes, instead of a scalar, I have a matrix W, and then that could be that is often known as a vector autoregressive model, where you have a vector of states xt, and then alpha becomes a matrix. And instead of directly relating to xt minus 1, all the information that was relevant for that particular um, uh, task at hand, I'm replacing xt minus 1 with ht minus 1. Ht summarizes everything from the past. And the typical neural network philosophy, I am adding a bias and a nonlinearity. Now, whenever we have a downstream task, YT would depend on the downstream task. So for example, HT need not be a scalar. If I'm doing a binary classification like sentiment analysis, yes or no, hit flop type of things, YT would be a scalar and it would be a 0, 1 or a smoother version of a 0, 1, like a sigmoid, for instance, right? But HT could be, we could reserve a larger memory for HT. So HT need not be a scalar. It could be a vector of any length. And again, a quick recap about the dimensions. So suppose we have the state to be P length vector. W would be of n times P. This, so now whatever I have not highlighted, or the ones that I will highlight in the blue color, that those are the parameters that you would learn to preserve the states. Now, transforming the states to the desired output, hit or flop, or say prediction, that we are doing a k-step prediction, would basically mean that YT would be k-step prediction as this vector. This would be a k-length vector, right? So because can you hear me? All right.
Yeah.
I think,
Yes, sir.
yeah, there was an outage, but okay. So let me rewind and tell what I was trying to say in the last half a second. Was that whatever I've highlighted in blue is the parameters that we are trying to figure out. So basically, we'll have to add all these n times p, n times n, n times 1, and q times n, and q times 1. You add all these numbers. So these are the number of parameters that we would like to learn to train an RNN, right? A single layer RNN, which has multiple outputs. If q is 1, then you have a single output, single recurrent neuron. So actually, n is equal to 1 means a single recurrent neuron. N greater than 1 means it is a recurrent neuron that has, there are more outputs to that recurrent neuron. So although there is no theoretical evidence, it is from observations that the typical length would be about, that it preserves the memory is about 10 steps. So there's no longer memory. So if I want to do a prediction, for instance, at xt plus 1, and that xt plus 1, whatever the behavior it should exhibit at xt plus 1, was depending on, say, 100 samples before, right? That is not possible with RNNs because the model is not explicitly asking anything of that nature, okay? So what that would also mean is that any long-term context will be lost, and the predictions that you would do would be based on the immediate samples. Although in theory, we saw that the state at t depends on the current state as well as a current input as well as the inputs all the way up to x0, but the influence would kind of exponentially decrease, right? So influence from the past would exponentially decay, and we would only have information from the last 10 or 20 samples, right? That is the memory that it can contain, and that is what we were also trying to pictorially illustrate through this what time is it now example, okay? So now suppose we will see later what is a fix to have a longer context information, and that is done through what is known as LSTM, and we'll see as we progress what is the particularity of LSTM. Okay, so now again some more illustrations to recap. Uh, so it's very simple. You use a simple RNN model. Instead of a dense layer, we are now using a simple RNN, and the you specify how many outputs the RNN should have. This is the length of that H vector. N in this case is 4, so it will have 4 outputs. And then eventually, you can ask whether we require outputs of each neuron, or we simply store or take a dump of the output at the last time step, right? So that is what we see here, right? So in this case, we only see the output at the last stage. But if you say return sequence is equal to true, this is particularly required for extending a single layer recurrent neuron to a multi-layer recurrent neuron, right? So what that does, in other words, called as a deep RNN. We will see what that is. But in this case, if you look at what is the delta between the top two pictures, you have access to the states at each of the time steps. Okay, that is the main difference. Before, you did not have access to the output. You had access to the output only at the last layer. Now you have access to the output at the intermediate layers as well. Okay, so this is kind of the difference between a sequence to sequence and a sequence models, right, that we were discussing in the last lecture. So
Sorry,
now,
Professor. Sorry to disturb you. Can you explain one more time that parameter 4 in the last slide?
so if you
Yeah, this
recollect
one.
here, we had this n. N basically indicates what is the size of the state. So h, what is the length of the h vector? The way you should visualize any output is that there are 4 recurrent neurons, and each of these 4 recurrent neurons is giving you, say, 4 outputs. In this case, n is equal to 4. Although you see that as one big box, there are small 4 recurrent neurons within that box. That forms one layer. Now, that is what is illustrated here. So here, when I say 4, it means that there are 4 recurrent neurons. As a consequence, you see that the output is of length 4. You see, like 1, 2, 3, 4. Okay. So now, what the difference between these two is that although both of them are recurrent neurons, which have 4 neurons, it's a single layer, right? It is a single layer, as we have written here. It's a single layer of RNN. Each in that single layer, you have 4 recurrent neurons. That means that you get 4 outputs. Okay. The difference between the top and the bottom is that in this case, we are not tapping the outputs at each time. So this is t is equal to 1, t is equal to 2, t is equal to 3. So if you look at the sentiment analysis, you were interested only in the output at the last layer. Having seen the sentence, you would want to make a decision, yes or no. Okay. So that could be, for instance, an application. The other application, like what I was trying to say, was now, for example, I am Groot. So now in this particular case, you would like to make a decision based on output at each time. Okay. So now what would that mean? So here, basically, I'm giving the output without doing anything, right? So output, you're simply passing the output of the last layer as the output. You could do an MLP on this. It could, for instance, you can do a dense of layer, for instance, right? So, dense of layer of X, right? With whatever one neuron and then layer of X and then some sigmoid, right? So that could be your output. So you can basically do an MLP of this output to make some decision, right? So yes or no type of decision. Now, whenever we have output that we tap at each time instance, you can make use of each of these outputs to make a decision. For example, I can have an MLP, like what we see here. This is an MLP, this is an MLP, and this is an MLP. But now if the decision is the same, right? This is a subtle tweak around the same idea that we were discussing. So suppose I would like to do a sentiment analysis, but now I don't want to only make a decision based on the output of the last layer, but I would like to make a decision based on the output of each layers, but the decision-making layer or the decision-making unit is the MLP. And I would like to use that same MLP, which is basically doing a hit or a flop decision, right? So the task of that MLP in sentiment analysis is decide, given an input, decide, hit or flop. Okay, that's a common that's the task of that MLP. Now, if we don't have return sequence is equal to true, the input to that box which decides hit or flop will be the output from the last time instance. Now, an alternative view is that I can give the input as input the output of RNN at each time step, but the box is the same. Okay, the weights of the box is the same. So that is elegantly implemented as a time distributed layer. So you have an MLP that takes 4 inputs and gives 1 output, for instance. But now, if you want to do weight sharing, I want to replicate the weights across all time instances. That is implemented as a time distributed layer. So instead of taking just one output, it takes multiple outputs. So it has more features as inputs and gives you an yes or no. So in other words, you're basically doing parameter sharing of that decision-making MLP. And that is nicely implemented as this time distributed layer, right? So now if you remove this time distributed layer, what this would basically mean is that I have a dense output layer, right? So you now can time distribute it or do a parameter sharing of that MLP that decides. So this is another nice feature that you should be aware of. Okay, so I hope this is clear. So return sequence and time distributed layer. So suppose you would like to reuse that MLP without dedicating in other words, like in simple words, suppose this is the weights and biases of this MLP. This is weights and biases of this MLP, and this is weights and biases of this MLP. What time distributed layer does is it forces W1 is equal to W2 is equal to W3. Okay, in simple words, that is what it does. So instead of you forcing that, you can basically use this time distributed function to enable this. So this also means B1 is equal to B2 is equal to B3. So it is going to learn the weights with this constraint. Okay. So these are two important features that is often very useful when we are coding a recurrent neural network layer.
Professor,
So
just
now,
one small
yes,
question. So if the time distributed is not there, so you meant that W and B's will be changing for every iteration, right? For the dense
correct.
layer.
So yeah. So see, suppose what time distributed is doing is it is tying the weights of all these dense layers, right? So now imagine the case, right? So let's think about this scenario. So I have these 3 time instances. Okay. And now suppose at each of these 3 time instances, your task is for each time it is varying. For example, at T1, you would like to do an yes or no. Time 2, you would like to do hit or flop. Time 3, you would like to do male or female. Okay, so an example to convey the message. So in this particular case, at each time instance, since the task is different, the MLP or the decision-making layer, that should be different. Okay, now in contrast, suppose at all time instances, your goal is the same. It is simply to decide whether it is male or female, right? Based on this sentence, I am Groot. So in that case, although you have 3 different MLPs, the goal is common, which means that although it is processing inputs at different time instances, it should be one common, since it has one common task, the decision-making unit should also be the same. So that's why this time distributed layer, what it does is it tries to tie. That is what this gray box means, right? So it is basically tying all these 3 different MLPs, although it appears different. When I do time distributed, it basically means it is the same MLP unit. Is that clear?
Yeah, okay, Professor. I need to go through more. Yeah.
Yes, Tripti.
So in this time distributed, we have to do it at the last layer, or we can do it in between also? How does
No,
it
so
matter?
so the moment we give return sequence is equal to true,
Mhm.
the output that you get is now not just 4 times 1 vector, but it will be 4 times 3 vector.
Three vectors.
You see? You see the difference? So
Okay.
now this 4 times 3 vector is going as an input to something.
Mhm.
Now, if I simply put a dense layer at this point, what it does is it is processing these 4 times 1 vector as say 3 times 4 matrix with 3 different MLPs.
Okay.
Okay, so now if you add time distributed layer, what it does is it is basically saying that although you have 3 different MLPs, if the weights are the same, that unit is the same.
Okay. Okay.
You see, uh, you see the difference?
But during model training only, these weights will be differing, na, Professor? Not in prediction or inference part.
No, so yeah, I mean, if we are forcing the weights to be the same during training, so what it does is now instead of learning these 3 weight matrices, it will only learn 1 weight matrix and 1 bias. And during inference, we'll also be using the same weights and bias that we train.
Okay. What?
Yeah.
So you meant to say for this dense layer, the weights and biases will change with respect to time variable. If this distribution
Yeah.
layer is not
If we,
kept.
yes, precisely.
Okay.
Okay.
But
Yeah.
other parameters will be same, like they won't depend on the time. Only this dense
See, I
layer
mean,
will be different.
okay, so the way you should understand is this is kind of doing the simple RNN layer is doing the feature extraction over time. And now I get this output. I need to do some task with this, right? Now, recall what we did with CNN. Although we had like many convolution layers, at the end there was an MLP layer always to do decision or to put a bounding box. Now, similarly, I have an RNN which is extracting features across time. Now, I need to do something with that feature, like a classification or a regression. That is done with an MLP layer. And that is what this dense does, right? And now the question is, do I need to process the outputs at each time instance with separate MLPs, or do I need to use the same MLP? And one way to do that is like you manually use dense and say that, okay, the weights are the same. This time distributed is basically doing that for you as a function.
So
Okay.
just a quick question, Professor. So if the time distributed is not used, so there will be a huge memory requirement, right?
Correct.
To store.
Yeah. But
Okay.
also, yeah, huge memory requirement, but oftentimes that is not what one would like to do. You would not,
Okay.
your task is not changing per
Yes.
time instance,
Yes.
right?
So
So I
we'll
give
be
you a
using by
sequence.
default. Yeah.
Yeah. So, I mean, yeah, so this is like 99.9% of the time, you would process sequence with a one task.
Yeah. Understood, Professor. Thanks. Yeah.
Yeah.
Thanks for that.
Okay. Okay. So now,
Professor, sorry, in the last slide, why the shape was 3/2? Input shape, why it was 3 by, how we have
yeah,
derived
so
it?
Yeah, so basically what it says is what I had also mentioned in the last class. I'm basically representing each of these words with a two-length vector.
Okay. So that's
And
a
3 means that every example has 3 time instances.
Mhm.
So this is 1, 2, and 3.
Okay.
Okay, so T is equal to 1, T is equal to 2.
Okay.
If I'm
got it.
processing a sequence of length 10, this will be 10 times 2.
Okay. Thanks. Got it.
Okay. So that means that every example that I get, so this is not giving a batch size, right? So the batch, you might have already realized this, in Keras, the batch is kind of, you don't have to specify it, but it basically figures it out based on the input that you give, right? So, but 3 would basically say that every example, so I'll have like many such sentences. So I am Growth, I am Sandeep, I am Tripti, I am Rajay, etc. Right? So I have 100 examples. And each of these examples are of length 3. And each word, I'm mapping it to a length 2 embedding vector.
Professor, but not in all cases the size will be same, right? The time frames will be same. It will be different. Arbitrary length will be there, right? Or will it be same, or we will fix it for RNN?
Yeah, so it will, you would use a windowing, right? So that window length would be fixed. You would process every time a length of, say, window 3 in this particular case, right? You would process 3 sentences and then you would go to the next chunk.
Okay, okay, thanks.
Yeah. Okay, so now, now moving forward, once we have understood what a recurrent neuron is, and it can output multiple recurrent neuron can have multiple outputs, the extension of stacking many recurrent neurons is kind of straightforward, given that we now know how to go from a single layer perceptron to a multi-layer perceptron. So in principle, all you need to do is do the same thing twice, right? You stack one below the other, with a caveat that whenever we are stacking one recurrent layer below the other to get a deep structure, the previous layers should have the return sequence is equal to true, so that that connection can be made. So you need basically the outputs at each of these time instances, and then only then you can put one layer below the other, right? Because now if you put simple RNN, two of those, so it means that you have a two-layer RNN. Now recall the input to the first layer is the time instances. There are, say, 3 time instances in the previous example. Now the second layer is also expecting 3 time instances. In case you don't set a return sequence is equal to true, you only get one time instance output, right? So here it was expecting 3, but you only have 1. But the moment you make return sequence is equal to true, you get again t is equal to 1, t is equal to 2, t is equal to 3. So 3 inputs become 3 outputs. Now this forms as input to the second layer. Okay, so that's the subtle difference whenever we have to stack multiple layers. So make sure that you have return sequence is equal to true in the previous layer. Now, why do we want to do this stacking of multiple recurrent neurons? Because it generally improves performance. With a very similar analogy, with a single layer, you have limited decision boundaries that we can identify. More deeper, in general, you would identify better decision boundaries, the performance increases. Okay, so once we know what is a single recurrent neuron layer, going to multiple layers is kind of straightforward. Now, recall we were discussing this example of predicting one step ahead. You basically can do it with a single RNN layer or a multiple RNN layers. So again, this is like a pictorial illustration of what is going on. So you have two layers of recurrent neurons, each outputting 4, right? So this is again length 3 times length 2, and the output is 4 times 1. That goes as input. Now, what that basically means is here we had like 3 times 2. Now we have 3 times 4 as input to this layer. Okay, again, the output is 4 times 1. But at the last layer, we don't have return sequence is equal to true. So that's why you don't see anything here. If I want 3 layers, then you would also make return sequence is equal to true for the second layer, and then that goes as input. Okay, I hope that idea is clear, right? So basically, to enable deep RNN, you require this return sequence. And that's also kind of logical to see that, okay, I need some input that I need to pass on to the subsequent hidden layers. So what we have now is like a one hidden layer. One
Sir,
hidden
so one question. So
layer.
for the hello, sir, can you hear me?
Yes, please go ahead.
So I thought this return sequence is only significant for the last output layer, whether you want to make it a sequence to vector kind of output or sequence to sequence output. But for the hidden layers, I thought default it should be return sequence is kind of true, right? Because if you don't do that, let's say if we don't do this in the hidden layer one, right? Then how would that work? Because by default, let's say I have two hidden layers and I don't have the return sequence
So
equal to true, then how does that work? Because that means that not
yeah,
all this.
it will throw an error.
Okay.
Yeah.
So
So
it is by default.
yeah, I'm
Sorry, sir.
emphasizing this because the default setting in Keras is return sequence is equal to false. Say, for
Okay.
example, in the last layer, I'm not specifying, for instance, see, I mean, Keras has two interesting arguments. So the input shape, oftentimes you need not specify. I'm giving it here to make the illustration bit more clear, right? So I have 3 time instances and 2 embeddings. That's why I'm giving. But default, you need not give this. It is going to automatically figure that out from data. Okay, the input that you give. And the other default setting is return sequence is equal to false. So if you see the last third line, just by doing this here, it is automatically going to figure out that the input shape for this particular case is now say 4/3. It's automatic. I don't have to specify. And that's because like for every hidden layer, I cannot keep on specifying, computing the hidden shape before calculating that before and specifying that, right? It should automatically figure out. And I cannot use two different functions for input and hidden layers, right? So that is the, I guess, the philosophy behind why they take it as a default, reading it from input data. Return sequence is equal to false is the default setting. I don't know why that is true, but I think, yeah, that's how it is coded.
Okay, got it. Thanks.
Yeah. So now, yeah, I mean, again, like, yeah, so here, as you can see, this is again like a sequence to vector model, except that why is it sequence? If you look at what is going on, you get a vector output and then you feed a sequence. Now, it doesn't matter if inside this box, there are like different architectures or different ways that the data is being processed. If you look at what is the input-output relation, input to the box, output of that box, this is still a sequence to vector. Okay, just to answer that last question of yours. So let me take, if return sequence is not true, then it will give the output at the, yeah. So yeah, in this particular case, the only thing that will be available to you is, see, I mean, these outputs that I will shade now will not be accessible. It is maintained internally, but eventually the output that you get would be this one. Okay. So because you're not giving return sequence is equal to true at the last layer. Okay. So that is what you would be able to process. And it'll not take average or max. It will simply give the last output, right? So like what I have highlighted here as output. Yeah, so loss function, maybe I can repeat again. So I did this already in the last class. So suppose in this particular case, right? So I would like to do a one step ahead prediction. So we have basically data from x0 to x51. Now the output, let's call it as O at time 49, okay, for a particular example I. Now you want this close to x50, right? This is the loss function. Now this, you don't worry about the sign of the error, you worry about the squared error. So you do a mean squared error, and this is for that last output, right? So I would like my last output to be close to the output at 50, and I would average this over all possible training examples. Okay, so this is 1 over tx. So now if you look at what is the loss function, this is a function of all the weights and biases of the recurrent neurons, right? All the Wx, Wh, Bh, and so on, right? So that is the loss function.
Sir, just one question on this.
Yeah, I'll just finish off the,
Go ahead.
yeah, if it is related to this, yeah, go ahead. Yeah.
Yeah, related to this only, would the loss function be different if it is sequence to sequence versus sequence to vector? The reason I'm asking is because sequence to sequence, for each time sequence, your prediction will be different, right? And then if you use this formula, then the loss will, you'll keep adjusting the weights for all the sequence, all the neurons. So with
So
time, that change, right? So that's the reason I'm
yeah,
asking.
so yeah, in the general message is that whenever we are dealing with a supervised learning problem, the loss function will only depend on the task at hand. Say, for example, if I'm doing a classification versus regression, the loss function would change, right? Now, again, sequence to vector, the goal is, for example, if it is sentiment analysis, what you would do is like, okay, you have an output, say, I would like, let's go back to this particular illustration. So I'm seeing output 3 layers. So here, let's call this output as O, and this output, you're mapping it to say a 4 length vector. So let's use the same notation. So HT, and then that becomes say, so this is like 3 to 1, right? So I would use a 3 uh, to 1 transformation. So in this case, I have like a HT is of length 4 times 1. And now I need a WY vector transpose. This is 1 times 4. This is going to give me there's some BY. This is going to give me a scalar, which is 1 times 1. Now this is, if I use sigmoid here, this is going to be between 0 and 1. Now what you do is you match this label Y to the true label, right? So this is for sequence to vector. It is basically doing a binary classification. In this case, you would use a cross entropy loss. Now you would not use an MSE loss in this particular case. So this is for sentiment analysis, right? Yes or no type of answer. Does that clarify your question?
Yes, sir, yes. Thanks.
Okay. Okay, Rupesh. So again, this is like not very specific to recurrent neural networks. This is specific. This is the answer that I will give is generic to any neural network deep learning training model. So what generally happens is that whenever we are training a recurrent, whenever we are training a neural network model, the function is often non-convex, right? It can have a crazy shape. Now, it so happens that most of the cases, the local minimas that we get are already good enough to make us happy. You don't even go towards a global minimum, right? So most of if you are looking at this particular landscape, say for example, what you're doing with gradient descent is you drop a ball, and the ball basically would settle down in one of these valleys, right? Now, this is what you would be happy with, and with this the accuracy that you get is already say 95%, you're happy, you don't care further. Maybe if you go towards the global minimum, you might get say 98%, but most of the most of the results are already useful when we are at local minimum, right? So that is the general happiness index with respect to training of neural networks. Of course, the desire is to go towards global minimum, but the local minimas are already good enough to for most of the applications that we envision. Okay, Rajai, you had a question?
Yeah, Professor, if you go back to the slide, this one. So here,
Okay.
in the second layer, the input shape, no, yeah, this one. So the input shape will be 3:1 rather than 4:1. Because we have for 3-time instances, we have input.
Yeah, so this is like 1, 2, 3, 4.
Okay.
3.
But we have 3-time instances, right? So it will be like.
Oh yeah, I mean, okay, you mean like yeah, it should be 3, 4, not 4, 3.
Yeah. Okay.
Yeah.
And then if I set return sequence false, so I mean, I will not be getting these two in between outputs, right? I will just be getting the last RNN one.
Yeah, so I mean, just like what we have in the last layer, right? So you don't say anything. You don't have to say return sequence is equal to false. It's a default setting.
Okay.
In this particular case, you see that you don't have anything here,
Okay. Yep.
right? You only
Thanks.
have the last one.
Thanks.
Okay. Yeah, so now if you don't give return sequence is equal to true here, then there'll be, yeah, it is expecting. So what it'll do is it'll start processing by default and it will throw an error.
Thanks. Thanks,
Okay.
Professor.
Yes, Jayanti.
Professor, I mean, just to, get the understanding with an example. If we look at a video of a road and we see how many people have, I mean, the entire video of the entire day, and we want to make a classification, how many people have crossed the signal, rather broke the signal, then that is that in that case we would use return sequence is equal to false. And if we want a real-time update of every hour how many people have broken the signal, in that case return sequences will be true. Is that correct?
No. So okay. In the first case, like okay, you're processing data which is a day long,
Yeah.
or an hour long. That is our 3 here.
Okay.
3 would become say 60, or say 24 times 60.
Okay.
And that has nothing to do with the return sequence.
Oh, okay.
Okay, so that is how long the data I would like to process.
Mhm.
Now, return sequence so now for this particular task, do I want to use a single layer RNN
Yeah.
or a multiple layer RNN or a deep RNN? If I would like to use a deep RNN,
Yeah.
say with 4 hidden layers,
Yeah.
then the first input layer will have a return sequence is equal to true. Second, third, and fourth will have return sequence is equal to true. The output layer
Yeah.
now is about predicting a number,
Yes.
and predicting a number being the number of people crossing the signal, right? A
Yeah.
particular. Now, in that particular case, the return sequence will be false because you are interested only in the output, that being a number, and you would like to do that at the end of your time horizon of interest,
Okay.
right? So, for example, like, yeah, you're still processing, say, an hour data,
Yeah.
and you would like to predict how many people crossed every minute,
Yes.
right? So the input length is 24, and the input length is 60, and the output, you would like to predict number of people crossing every minute. Then even for the last layer, we'll have a return sequence is equal to true.
Okay. Okay.
Okay. Now the decision-making MLP, which is basically transforming the hidden state to the number.
Yeah.
Now that box is a common for every minute,
Okay.
right? So it is basically taking hidden state and giving you a number, right? And that number is the number of people. So that task, since it is common for every minute, I would use a time distributed layer.
Okay. Okay.
Okay. Now, in case you're not interested in predicting the number of people crossing this junction every minute, but
Mhm.
only at the end of an hour,
Yeah.
then you process 1 hour data, you keep accumulating, and then, okay, the last output, you pass that through an MLP that is going to transform. It will be a single MLP that is going to transform the hidden state to that number.
Okay. Okay.
Okay, make sense?
Yes. So the difference is only in the last layer, whether the return sequences will be true or false based on between these two.
Right.
Okay.
Yeah.
Thank you.
Yeah. Okay. So I hope there are no further questions. So let's proceed further. Now, recall, again, a quick recall that what time is now with that example. If you look at the memory of this recurrent neuron, at each time instance, the color for T0 was kind of diminishing here, right? So if you look at this, time, it has an influence from what and time 50-50. But then when we are looking at ease, the influence of what was diminishing, right? So that was the length of the memory that an RNN can hold. And experimental evidence says that it's about 10 to 20 steps. Now, think of this example, right? So just don't worry about the dense slide at this point, but let's take this particular example, right? So I have this long sentence, say, Mr. Bob, although this is like 10 is just a number, but imagine as if this is a very long sentence. So Mr. Bob has a background in arts, but now I would like to use a pronoun if it is a he or a she, right? But he is now an engineer, right? So if that is a sentence, Mr. Bob has a background in arts, but I will have to predict what that sentence is. Now, to put a he or a she or an it, I need to remember what was Bob, Mr. Bob, right? It's like, okay, so I need to remember the context in this particular case is a gender. I need to recall that proper. Now, in this, although because I didn't want to make the slide even more denser, I put this sentence with a few words, but imagine that, okay, you are reading a very long sentence, and then Mr. is not becoming Miss Alice for a long time, right? So I have like a paragraph talking about Mr. Bob, and then all of a sudden, Miss Alice comes, right? So Miss Alice has a background in science, but she is also an engineer, right? If that is the sentence, now the network, the way we work is we keep track of these keywords, right? Mr. Okay, now the pronoun should be he and so on. And as soon as I see the change in the context, Mr. Bob becomes Miss Alice, then I should basically remove that Mr. context from my memory and introduce Miss. Okay, so I need to specify that something has to be remembered and something has to be forgotten. Okay, now Mr. Bob, he, as soon as I encounter Miss, it becomes a she. Okay, now we have this, for example, in the training data. Suppose I have these many sentences, and sentences, the training data is basically, if it is like a next word predictor, say for Mr., there is a he, Miss, there is a she, right? So the next words, the pronouns would be he's and the she's. Okay, so I hope that example is clear. Now, if we do this with RNN, if the sentence is more than, like, say, 10 time instances or 10 words, then that Mr. would be forgotten, and then there's no influence of the first or the word that was like 20 time instances behind. So it fails. Now, to enable memory over long-term patterns, a simple variant of RNN was proposed. It is called LSTM. And wherever people still use RNNs for whatever time series analysis, etc., people would by default use LSTM. RNN, although it is one of the first models, very simple ones, it's not often used in practice. LSTM, or a simpler version of LSTM that we will see later on, the GRU is gated recurrent unit, is the most common used model. It basically handles the limitation of RNN that I mentioned, where it specifies what has to be remembered over a long term and what has to be remembered over a short term. Whatever RNN was doing was a short-term memory. So now let's break this down into several simpler modules. But if you're interested only in the math behind what, or you only, okay, if you're interested only in the code behind what is going on, all changes from a simple RNN to the LSTM is basically this particular word. Simple RNN becomes LSTM. Nothing else changes. Everything else remains the same. Okay, if you're happy with that, that is all the simple change that you require, with the additional feature that you're now slightly increasing the memory length. How is this actually done in practice? With the following different so-called gates. What is the main distinction is the following. We have the short-term state as before. This is what RNN was trying to do. Okay. Now, to preserve something over a longer horizon, LSTM introduces this additional new state. If I want to remember over a longer time, remember this example of fading memory that I gave, right? So, okay, if you want to remember what you did 1 year ago, unless it was a special day, like your birthday, anniversary, etc., you would not pay specific attention. And if it is something special, you have a memory or a memory allocated to remember that particular thing, right? If you want to remember phone numbers or etc., you put an effort to remember that over a longer horizon, right? So you don't easily forget. So a similar notion is introduced here, where there is an additional state called as a long-term state, which is introduced in LSTM. Now, HT is what is before, right? So simple as simple RNN. The input to this LSTM cell is twofold. CT, you don't have access to that, you don't see it. It is internally maintained in an LSTM unit. It's still a recurrent neuron in the sense that it takes the input from the current time and the state from the previous time. CT, although it is shown as a specific input, you don't have access to that typically. It is maintained internally, but You have something from the past, something from the current. That philosophy is still the same. Now, let's focus on what is going on with the long-term state. So let's focus on this particular equation here. Now, if you look at this, the idea is the following. CT should be either 0 or 1. Since 0 or 1 is that step function, we use a smoother variation of that. And CT, whether it should be changed or retained, is defined by two particular gates, which are the forget gate and the input gate. Okay, so suppose the sentence was regarding Mr. Bob. Okay, then the forget gate basically remains unchanged, which basically means that CT will be equal to CT minus 1. I don't have to do anything. I don't have to forget that memory from my unit. I still have to retain that memory. The moment Mr. Bob becomes Miss Alice, then the output of this forget gate should be 1. The old state should be forgotten, flushed out of memory, and the new state should be written into the memory. Okay, so that is the basic idea, right? And these are basically done through these gates. So forget gate is basically removing, flushing something out of the memory, and the input gate is writing something to the memory. Okay, so now if it is Mr. Bob in the sentence, the forget gate would be simply 0, and whatever CT, the state is maintained, is due to the input gate being 1. Okay, so for the idea is that if forget is 0, input should be 1. Okay, now suppose Miss Alice comes, then forget would be 1 and input would be 0. And it is not simply a Boolean operation, a 0 or 1, but it is an influence from the output of a MLP. Okay, so all these boxes that you see here are multi-layer perceptrons. Okay, so there are 4 multi-layer perceptrons. Each of them are like a recurrent neuron where it takes input from the current time, something from the past, and the bias. So you see that now I have 4 times as many recurrent neurons as what I had before, which also means that the number of parameters in LSTM is 4 times the number of parameters in RNA. Okay, so to put that extra effort to maintain something over a longer horizon, we are increasing the number of parameters. Short-term state is something that we had before. Let's now go through each of this. Imagine that I have 4 times recurrent neurons as before, with all the W's and the B's for an X and a H. Input gate, the role is to look at the current state and the previous state to see if I need to change the context or not. Forget gate, the goal is the same. The way it is envisioned to train is that whenever the forget gate is 1, the input gate is 0, and vice versa. The output gate is basically what determines the final HT state or the final output. Here in this particular thing, we are using YT is equal to HT, but otherwise, you can also have another set of parameters to differentiate between YT and HT. Okay, so there are a few more things going on here, which are color coded, which basically tells that F and I and O should be between 0 and 1, and tan hyperbolic is the activation function that is used at the GT. Okay, so this is what is going on. So the main message is if you want to remember something over a longer horizon, you need to reserve a memory unit for that. And that is precisely what the LSTM does through introducing these 4 recurrent neurons, each with a dedicated task. And most importantly, you have a long-term state and a short-term state. Short-term state is the short-term memory that RNN was always having. Long-term state is something that you would like to maintain over a longer horizon. Okay, so the number of parameters is increased by 4-fold. The main cell is basically the same as the RNN, right? So now long-term and short-term states are the states that you maintain in a LSTM architecture. Okay, and this is kind of by default the sequence modeling architecture chosen if one chooses to go with LSTM. Although oftentimes nowadays people prefer transformers for many applications where one does not have access to heavy compute, right? So for example, to use all these transformer-based GPT models, etc., you might not have enough inference time, or you would like to operate on an edge device to do time series analysis, like some of the examples that I will hopefully show at a later point of time, where the anomaly detection based on for a fault diagnosis in International Space Station is using an LSTM module, right? So you would not put a GPT there, or anything that is not text attributed, you would not go with GPT-based models, so transformer-based models. But if it is like sensor data in a health or a factory setting where you are doing fault diagnosis, you would still go for these older versions of sequence models compared to say transformers, etc. If you are dealing with text attributed sequences and you have enough memory for inference, then you would go with the GPT models. But LSTM is kind of the default for all these time series analysis tasks. Okay, so now let's take this poll to just reflect what we have been doing so far with LSTMs, and also try to and appreciate the difference between LSTM and RNNs. Again, like the software wise, the only change that one would do is the simple RNN would be changed to an LSTM.
Sir, could you provide practical use case of when we should use simple RNN and when this LSTM will be preferable?
So for simple examples, right? So whenever you don't require, say, I mean, for example, right? So for if you're doing weather prediction, right? There's not much to remember from the long term. Then you would not use LSTM. A simple RNN would do the job. But if you want to have, say, a long-term context information, like, say, for example, this music generation example that I showed in the beginning of the last lecture, there, it's not just the immediate previous 5 to 10 notes, but you want information from a longer horizon to be maintained, right? What is the pitch scale, etc. Right?
Yeah.
So that if it has to be maintained, then you would use LSTM. And as I was telling, LSTM is kind of the by default choice.
Mhm.
The only difference between LSTM and RNN, LSTM only performs better, but it comes with a cost, right? It is 4 times more parameters. Now, if that cost is affordable, then one should simply use LSTM. And
Okay.
there is a slightly simpler variant that I will introduce before we pause for the break. It's a
Sure.
subtle, slight difference. So LSTM and GRU are kind of by default choices.
Okay. Okay.
So
GRE is
if so,
also
even if you don't require say a long-term context information and you use LSTM instead of RNN, LSTM would not do any damage.
okay. Yeah.
Yeah.
Thanks. Yeah.
Okay.
Thanks.
Yeah. So let me conclude this poll. So yeah, just to uh, again recap, we maintain two states, one for the long term, one for the short term. That's the main difference. Yes, Vikas.
No, I just have one confusion. So in both LSTM and simple RNN, you were talking about in each of the simple RNN, you need to mention true, false, right? But how do I decide that how many simple RNNs should be written or LSTM should be written? Is it as per the problem statement, the complexity of the problem statement, or there is something else? Sorry if you already explained and if I missed it.
You mean these four
If you go
blocks that we
to
see?
no, so in the top, if you have the model that is layers LSTM20, and at the end it is written sequence true, and at the same time you were mentioning you can have this
Yeah.
multiples, right? So
Yeah.
now how
So
do I
this is
decide
like
whether it is 1, 2,
this one.
or 10? Yeah,
This one, the 20 that you're mentioning.
it is
20
both the
that are high.
lines. In fact, if you go to the previous one, previous slide, right? This one is LSTM. Previous one is, I think, simple RNN. Yeah,
Yeah,
in this
4.
one.
Yeah, your
Yeah.
question is, yeah. So if you remember the discussion on choice of the number of neurons in a hidden layer, that was a hyperparameter, right? So the number of recurrent neurons in all the hidden layers is a hyperparameter, and that kind of signifies the size of the memory that we are allocating, right? So 4 times 1 would mean that I'm reserving a 4-dimensional vector. Now, suppose I would like to maintain something more complicated, you would slightly increase that. So it is the number of recurrent neurons. Now, the output, the last layer, is task dependent always. Okay. So again, yeah, here the output, it's basically like again transforming, say 4 to 1, right? So for this example of sentiment analysis, we had 4 outputs and we are transforming it to 1. So that is task dependent. So now if I go back to this LSTM, so here I would like to predict an output that is 10 length long, right? So that is what determined by the task. But the 20 here is a hyperparameter that you would choose. And typical choices are 10 to 20.
No,
But
sorry,
then
if I was wrong, my question is not that. It is about number of layers, right? So LSTM, the layer itself is couple of time,
yeah,
right?
so
So
that is again like a hyperparameter, right? So how many so the analogy is very similar to the discussion that we had during multi-layer perceptron. So how many hidden layers do we need to have? How many neurons do we need to have per hidden layer? That is a hyperparameter that you would tune for using validation data. So you would start with say 3 or 4 hidden layers, and then if you get a desired number of desired accuracy, then you start reducing the number of layers to see that, okay, now I'm getting this 90% accuracy with 4 hidden layers. Can I now try to get the same accuracy with, say, 2 hidden layers? The trade-off is more hidden layers, more recurrent neurons in each hidden layer. You are increasing the number of parameters that you train. So you use validation data to arrive at the right combination, keeping in mind the trade-off with the memory consumption that you can afford.
so when
Right.
I understand this would be iterative, right? So if it is iterative, what number I should be starting with? Is it the lower number go to higher, or go with the higher number go to lower? So
It is
basically what I mean
it
is
is
start
not
with 4, go to 3, or 3 to 4.
it is not it's not an iterative trial and error process, right? So if you remember the cross validation and hyperparameter tuning, there are these grids that you will have to give. For example, you can, I mean, simply think of the following, right? So suppose the layers that you choose are varying from 1 to 5, okay? And then the number of neurons per hidden layer is varying from, say, 10 to 30. Now imagine that you would make a grid, okay, of this two parameters that you search over, and then you visit each of these grid points through validation data. You don't manually do that, but that is automatically implemented as a grid search CV, a tool that would give you the right set of hyperparameters. That is kind of an exhaustive search, but often what is done in practice is so-called random search, right? So you do a random draw of these points within the space of number of layers versus number of parameters, and you arrive at the right set of parameters. So that's random search CV, right? So we had this discussion during the MLP, but the same holds also for this. So you don't start like with a small number and a large number, but you have a space of parameters that you search over. So that's called hyperparameter tuning, and that is something that cannot be avoided with these generic purpose black boxes. Okay. Yeah. Okay. Yeah. So me. Yeah. Okay. So maybe I'll do this gated recurrent unit, which is a simplified version of LSTM. And then I will look at that example that I was trying to show, and then we can wrap up. We are slightly overshooting in terms of the break time, but that's fine. So LSTM, as we saw, was introducing these 4 new gates, 4 new RNNs to basically write something into the memory and remove something into the memory. The main difference between LSTM and gated recurrent units, or in short called as GRU, is that the forget and the input gates are merged. Okay, so as you can see here, if the idea was that if the forget gate is 1, the input gate is 0, right? So for that, you don't require 2 variables. I can do it with 1 variable. As you can see, if this is 1, this would be 0 and vice versa, right? So the only difference is that the number of parameters from LSTM, GRU, and RNN, LSTM was a 4-fold increase. By merging the forget and the input gate, you now reduce the parameter to a 3-fold increase. So the number of parameters in GRU is 3 times the number of parameters in a simple RNN. Okay, so that is the main difference, where the forget and the input gate are merged. The remaining philosophy remains the same, right? So I would like to maintain something over a longer horizon, but to this common forget and input gates. So software wise, the only thing that changes is LSTM, GRU, or simple RNN, right? So you should be able to implement for any of the tasks with these 3 layers, right? So you would see the difference where RNN would deteriorate, GRU and LSTM would give better performance whenever, as I said, like you require information over a longer horizon. So this is like, again, putting this particular LSTM into action, where it is for, you can take a look at it yourself, but the idea is the following. You can do a model summary to get the number of parameters, like what we were discussing. Here it is an LSTM. The number of parameters are four-fold increase compared to a simple RNN. But the idea with this example is the following, right? So it is for predicting temperature based on some historical weather data. It has all these parameters, and there is some feature engineering going on where we remove certain features that do not particularly influence the temperature, right? So for example, like whatever this RHO, etc. is, we don't ignore that. Only those features are fed to the model. And this is a time series data. And the goal is to predict what is the temperature. So we start with, say, one hidden layer of, say, one LSTM layer. That's not a deep RNN. And then one dense layer in the output to say that, okay, how many outputs we require. So this is basically predicting the temperature at that particular instance, right? So you get one output. And you can do all the computations, but like what I explained, but doing a model summary would basically give you that information as well. Okay, so with this, we will pause now for a break. We'll resume back at, say, 10 minutes past 11, and then continue with the remaining part of the discussion, summarize the RNN model, and then we will switch gears to look at the autoencoder parts. Okay, now we'll pause for a break and then resume back at 10 minutes past 11. Okay, so let's resume back. Imut.
Yeah, Professor. I had a quick question. Before break, you explained that time distributed can be applied on, let's say, multiple, means on dense layer where we are having multiple neurons of that. If all of them are doing the same task, like spam or no spam, something like that, in that particular case. But when we were going through the concept of dense layer itself, it is like one neuron for each for one task. So I don't need three neurons for the example like you showed. Means in that particular case, is time distributed redundant?
No. So the way you should, again, like another way of understanding this time distributed layer is, see, I mean, while doing a binary classification of, say, email, spam, or ham, we had multiple. So there were two dimensions, right? One is the feature dimension, the number of features. The other dimension is number of examples. And for each of these examples, we were passing through the same dense layer to get some output. In this case, a Boolean output, ham or spam. And since the output was scalar, we had one output neuron. Okay. Now, if you require two outputs, you will have two neurons, but that's a different story. Now, the other dimension, that is the number of examples that we have, we were passing all the examples through the same MLP. Now, these examples were, you are showing these examples to the MLP as a part of your iterations, right? So the training epoch, you are making mini batches and showing 32 examples at once. Now, imagine the following. With the recurrent neuron, I have example, you have certain time steps. Now, all these time steps are acting as examples, and that is what you feed through the same MLP. Since it is going through the same MLP, we use that time distributed layer. Does it make able to interpret what I said?
Just the last line,
So
maybe. Yeah.
yeah. So when we have this So this time distributed layer that we see here, right? So maybe here, what is going on is like, so if you have these 4 different MLPs, and these 4 different MLPs doesn't matter like what. So in this particular illustration, the output size is 4 for whatever reason, right? The output size in the example that you mentioned will be 1. So you would just use dense 1. But the what time distributed layer is doing, it is treating all these as different examples. Okay, so it is using, so now for every, if you have n examples and each example has 3 time steps, the total number of inputs to that MLP would be n times t. But if you did not use time distributed, you will have tm. Each MLP will have only one n examples. Okay, so that's the difference. So
Okay.
all these MLPs are the same. And now you put together all the examples, so n times t, that is the total number of examples. If you do not use time distributed, you would have t different MLPs. Each of these t different MLPs would get n examples only, because you're saying that those are different, right? So MLP from time instance 1 is different from time instance 2, from time instance 3, which is not what we want, right?
Okay, okay. And Professor, in this mini project that we are currently doing, in one of the hints or somewhere I saw that there is a time distributed, just like here, the time distributed is wrapped over dense. There was time distributed wrapped over convolution 2D as well. So can you explain that a little?
Can I comment on that towards the end, just in the interest of time?
Yeah, sure, Professor.
Okay. So just to make sure that we are lagging behind. So now we'll be switching gears and starting the first concept on this generative AI models. Although autoencoders is not clearly a generative model, it is kind of an unsupervised representation learning method, where you would like to learn embeddings or features from input data in cases where I don't have labels. Okay, so you want to automatically encode data, so hence unsupervised. And some of the applications of autoencoders, as we will see later on, a subtle change in the autoencoder will give you something known as a variational autoencoder. And that forms the first principles behind generative modeling or what is the process, or how should I model the data generation. So for example, if we have this fashion MS data, what is the underlying generator to generate such fashion MS data, right? So that is what we are trying to learn through these autoencoder models. The name basically is a abbreviation of automatically encoding training data. So you would like to get a representation of the data without training labels. Okay, so far in supervised setting, we always had training labels. We were extracting features that were relevant for that particular task, because we were specifying the loss function, saying that the loss function was a discrepancy between the label and the output of the neural network. And we were asking that neural network to figure out features that were important for that task to get the accuracy high. Now, in this setting, we don't have training labels, right? So the loss function will be slightly different. Some of the applications are, as we will discuss, it is anomaly detection. So suppose you have this ECG example, you would like to automatically decide whether an ECG that you see is anomalous or not, right? So this is like a particular segment of an ECG, pre-processed tiny segment. You would like to figure out whether there is it's a normal ECG or an anomalous ECG. The other applications are, for example, like most of the data that we get are corrupted with noise, or it has missing data. Now, suppose I know what is the underlying process that generates the image. So I can basically go from such missing pixels to complete the image, right? So for example, this can be used for improving the resolution of an image. You capture an image with a low resolution camera, and then you would like to increase the resolution of the image. In usual cameras, that is not usually considered, but for example, if you're looking at hyperspectral imaging, where you are looking at images from satellites or drones, and the image resolution is a function of the rotation of Earth and the speed at which the drone or the satellite is moving, right? Although you would like to acquire a lot of images for a particular instant of time, but because of the motion, you don't have that time window, but you acquire images of low resolution. Acquisition time is proportional to the resolution, or resolution is proportional to the time. So in that case, you would like to kind of fill the images, right? So fill the missing pixels to get a better resolution. So in all these cases, if you know what is the generation process, what should I know to generate? So what is the model that is basically leading to an image that looks like this? Because if you look at any, say, known physical systems, if you have an input, you know what is the output, right? So if I transmit a signal here, I know how does the signal look at, say, a distance d, right? So those are typical signal processing problems where the input-output relation is explained through physics and differential equations. But if you want to figure out why a t-shirt is a t-shirt, is there a differential equation that explains what a t-shirt is? That doesn't make any sense. But now how can we learn the underlying generation process, which could be a bit abstract and cannot be explained using the usual notions that we have? So what is the data generation process, right? So that is what generative AI is all about. And towards that particular end, we will look at one aspect, which is autoencoders, and build upon this in the rest of today's lecture, and also continue maybe the GAN part in the next lecture as well. Okay. So before that, before we get started, let's try to do the simple exercise. I have these two sequences with me right now. As usual, I would like you to, a few of you to basically tell out of these two sequences, which one do you think is easier to memorize?
Second one, sir. 47, 45, 43, 10 pattern.
Second one, first one. And so more answers. So Jayanti, why do you say first one?
Second one.
Okay. I think the less number.
Less number. And many of them are saying second one. So maybe I'll just pick Deepa. Why do you say second?
Because it's in the sequence of +2 in the reverse order. And
Yeah. So if you look at although apparently the first sequence has fewer numbers, you might think that is easier to store, right? Memory wise. But if you look at the second sequence, all you need to store is the start and the end, and or start and the numbers, that how many numbers you want to generate, and the pattern. Okay, so that is like you start with 47, and then okay, I need to generate up to 21, how many numbers it is, and then all I need to do is what is the relation between the first one and the second one, second and the third, and so on. So basically, with three numbers in whatever format we store, you're basically able to generate the second sequence, right? So that is kind of a generative process. Now, of course, it will not be interesting to deal with data sets that are this obvious, right? So obvious obvious in finding patterns, but the illustration of how to figure out what is a generative process and what is the most efficient way to learn this generative process. Okay, so that's the basic idea, and then how do we do that, right? So that is what we will understand as we progress. So just to quickly put in one slide, what is unsupervised versus supervised? I mean, all of you should know this already, but so far, we have been discussing supervised learning, where we would like to send the input data to make a hypothesis through a nonlinear function. This could be a single layer MLP or a multi-layer MLP, or simply as simple as logistic regression, right? So some function which has some underlying parameters that is going to give you the labels, right? So you do this for every data in your training example, and by doing so, you figure out what this underlying parameter phi is, and once you have that, you get a test sample. Let's call it as X star. You would get estimate of your label. Okay. Now, to do this, you require supervision through Y and X. Okay. So you have the training data pair, input output pair, using which you learn the underlying parameters. You set up a loss function to minimize the discrepancy between yi hat and phi of xi for all i's in your training sample, and then you would figure out what phi is. Once I get a test sample, you have an estimate of your labels. This is supervised setting that we have been dealing with. Now, in the unsupervised setting, in the training data, there's no yi's. So I only get this big X matrix, which is features versus number of examples. No labels in training data. This is unsupervised setting. There's no supervision through the labels. Now, in this particular case, what we would like to do is we would like to efficiently compute the features. So imagine we had this convolution neural network pipeline where there were many convolution pooling layers. At some point, we had a dense layer that is going to transform the features to the task at hand. Now, the way we learned all the convolution filters as well as the dense layers was task dependent, because that is driven by the loss function at hand. Now, imagine I don't have that training label. Hence, the loss function that we typically define is not valid anymore. So in that case, how should I still extract the features that were up to that dense layer, right? So I would like to extract something meaningful, preferably encode that data, like what we did in the previous example, summarize that whatever was there in the data. Okay, so how do we do that? That is the basic goal of representation learning. So for example, like I would like to simply have a compact representation, and this compact representation example be used in, say, clustering, right? So when you're in clustering, you don't do any labels, but the clustering would basically tell that it's an unsupervised learning method where you're saying that, okay, this particular data has 4 clusters, but you don't have the information about what these clusters mean, right? So the clusters could mean that these are, say, doctors, engineers, architects, and some plumber, right? So you don't have that class information, but you know that, okay, there are these 4 clusters or 4 classes in data. So that is unsupervised learning. And often unsupervised learning is a very important data science tool, which is useful for visualization, for example, or dimensionality reduction. Dimensionality reduction was one example that we saw in the previous number sequence example. But imagine the following, right? So suppose I have this data matrix X, which has, say, n examples and p features. So features are, say, 1,000, and then examples are about, say, 10,000. Okay, now you would like to do some exploratory data analysis to understand what is going on in that data. So if we have a 2-feature case, like the picture on the left, where you're measuring some health parameters like weight and height, 2 parameters of these 6 subjects. Now, because it is a 2-dimensional picture, I can basically look at what is going on and put a class, right? So, okay, these are people who are shorter and and smaller weight, and then as the height increases, then the weight is decreasing. That is the distribution of the data that we have in the examples that we are looking at. Now, imagine I have 5 more such parameters. And if you want to visualize that data, that becomes highly complicated, right? Because human brain is not trained or capable of visualizing, most of us, we are not capable of visualizing something beyond 3D, right? So if I want to draw an illustration on this 2D plane, I'll use examples that are in R2, and beyond that, it will get messy, and even beyond that, it will be impossible to visualize what is going on in this data. Now, the goal behind data visualization and dimensional reduction is to reduce the feature size, not just by throwing away features at random, but arrive at a new representation. So instead of this 1,000 features, I would like to come up with 3 equivalent or 2 equivalent features in the reduced dimensional space. And in that space, whatever information was being conveyed in the higher dimensional space, that should still be preserved. Okay, so that is the goal behind dimensional reduction. So for example, here in this data, we have like 3-dimensional space, right? So there is like a set of green clusters, blue clusters, and red clusters. Now for visualization purpose, from 3, I would like to reduce the dimension to 2. So that means that the data matrix, which was say in the space 4, 7, and then 12 times 3 is being reduced to say x reduce 12 times 2. Okay, for visualization purpose, I'm reducing. Now this could mean, for example, say height, weight, and then age, right? So some 3 example dimensions, but this has some particular pattern in the higher dimensional space. Now, whenever we are learning these features, it is desirable that whatever geometric information that the graph was conveying in the higher dimensional space, telling us about data, is also preserved in the lower dimensional space. So those clusters, for instance, are maintained, but this would be an axis that might not physically mean anything. This need not be height and weight, right? So this is some new feature axis 1 and feature axis 2, right? So if this was say some units that were meaningful after dimensional reduction, you're only trying to see what is going on in the data in some reduced dimensional space, but the space or the underlying dimensions in the space might not have any physical relation as that was there in the original space, right? So this is what is called as an embedding. So you are basically taking data, embedding into the lower dimensional space. We already use this word embedding. For example, this I am Groot example, where I was put into some vectors, 2-dimensional vector I am was put. The idea is that whenever you get something like I, me, etc., so those are close by in the lower dimensional space as well, right? So from going from one space to the other, you're embedding into a vector space, and the information that was being conveyed in the higher dimensional space is preserved also in the lower dimensional space. So this is a general tool that is very useful for data visualization, right? So next to all this deep learning, AI, etc., to whenever somebody gives you a data, it is very important to first, before throwing a model, any of these models, you would like to first do some exploratory data analysis. You would like to do exploration. Okay, what is that I'm dealing with? How many, can I see some obvious clusters in the data? The features, are they correlated? Are they relevant to for the task that I'm doing? So just to uh, uh, get sense of what is going on, because you throw data at a deep neural network you train, it's going to give you some output. But now you also want to understand and interpret if that output makes sense, right? That is also a crucial task, next to explaining why you're getting those outputs. But to begin with, to understand if the output makes sense, you have to analyze the data, and data visualization is a very important tool in order to do that task. Now, there are two ways to do dimensionality reduction. The first way is through something known as a projection, okay? And tools like PCA, Principal Component Analysis, that many of you might know, falls under this category. So if you look at this illustration of what is going on, there is a set of points. Each point is in R3. That means it requires 3 coordinates, x1, x2, x3, to represent each of these points, right? So it's a 3-dimensional vector. Each point is 3-dimensional vector. But now, if you actually look at this picture and ask yourself, do I really require 3 coordinates, or can the same information be conveyed in 2 dimensions, right? So similar to the sequence example, there were many numbers, but now if you look at a way, there is a way to compress that, encode that, okay? So now, of course, given this 1,000 examples with 100 features, I might not be able to manually do that compression. We want an automatic way of doing that. That is where we are getting to. So now, whenever we are looking at this picture, what we can basically do is try to project this. How do we project? We don't know. When I project this onto this shaded plane, I get a new axis. So I'm not projecting on x1, x2, but I'm projecting on z1, z2 axis, some new axis, z1 and z2, and figure out what this z1, z2 is. And that is what PCA does. Okay. So if you look at this, if I project everything onto that z1, z2 axis, whatever information was being conveyed by these 3 points, now I can convey this information that, okay, this is distributed along this circular path, and each of this point now only requires 2 dimensions to represent. So that information is preserved. Okay, so that is the idea behind the first philosophy of doing dimensional reduction, PCA. And autoencoders are kind of generalization of what PCA is. The second common way of doing dimensional reduction is through something called as manifold learning. For example, TSNE is a popular way, right? So a popular manifold learning approach. So I'm giving you a gentle introduction to set up the context for autoencoders that we will cover rest of the class, and then also the next class as well. But these are two important tools, PCA and TSNE. These are algebraic, neural network based methods to visualize data, do dimensional reduction. If you look at any of the SkyPy package, you can PCA, you can do PCA of X and then tell how many dimensions you would like to preserve. Then you're going to get a reduced dimensional matrix, n times 2, right? In that particular example. And you can now do a scatter plot, do a visualization. TSNE, again, you give data, you tell how many dimensions you would like to eventually have. It is going to use some other algorithm that will not go through in detail, but it is going to give you a visualization, a matrix that you can visualize, right? So that's the basic idea. You take data and then how many dimensions as input, feed it through TSNE or PCA. Both these use different algorithm and different philosophy. In manifold learning, the idea is that you cannot simply maintain whatever information was there in the higher dimensional space by just doing that linear projection operation, but you can do something known as a manifold hypothesis, which basically tells that if 2 points are related in a higher dimensional space through some measure, geometric measure, they should also be preserved in the lower dimensional space. That is the manifold learning hypothesis that TSNE uses. Projection is simply using a linear operation. You project, simply drop the balls. For example, in this particular case, if you do projection and each of the colors in the Swiss roll example would mean that data points belong to different classes. Now imagine that I simply drop this on some axis, right? So on the vertical plane, x1, x2, then all these colors would get mixed up, right? So you would get a mix of these yellow and red dots. Now, the other way is, if I want to preserve that, still project it on, or still reduce to a lower dimension, then you could do the same by unrolling the Swiss roll, which is kind of a nonlinear operation, right? So that is what manifold learning or TSNE does. And in this particular case, you can still separate the classes that are out there. Okay, so TSNE, if you're interested, you should look at what TSNE is and what PCA is. PCA will talk a bit more about this PCA to introduce this autoencoder. So what we have seen so far is that data visualization is super useful. There are two ways, two philosophies basically, projection-based and manifold learning. Projection-based, popular method is principal component analysis, whereas manifold learning, the hypothesis is projection is not always the best approach, and you would like to preserve the geometric distance, not just by doing a projection, but by doing some complicated operation, and TSNE is a popular way. And oftentimes, what could happen is, I'm going from, say, a feature matrix, which is n times 3 to an n times 2. After doing this feature dimensionality reduction, the underlying problem could become simpler. For example, you look at this, right? So here, if I'm looking at a classifier that is more complicated, right? So that is also kind of nonlinear. The classifiers that we get can be much more simpler, right? So it results in a simpler solution. I'm reducing the training data, throwing away redundant information. Hence, I can improve the inference and the training time. Okay, so just to put these thoughts together, let's take up this quick poll question before we proceed further. Okay, so just to summarize the thoughts that was conveyed, I'll keep this poll short and end it soon. Yeah, so the answer is, of course, like you can do it by projection or manifold learning. It reduces the training time and results in a simpler solution for the downstream task. Okay, so I'll go into the details of what principal component analysis is, right? To set up this context of autoencoders. I'll not go into the details of this, but the idea is the following, right? So suppose, let me see if I have the. Yeah, so suppose I have a data which is, say, n times p features, okay? Now, I would like to simply project it onto a one-dimensional space. The way I can do that is through a linear operation, a simple linear operation, multiply this with some vector x times w. Okay, so if I do this, then what I get is this x vector in a reduced dimensional space, which is n times 1. So I had P features. I'm multiplying this with a P times 1 vector. That is going to give me a reduced set of features. So I'm reducing P to 1. Okay, from X, if I deal with X reduce, I'm reducing the number of features to 1. And I do this for every example N. Okay, now there are many ways to do this. Now the question is, what is the best way to do this projection and how to find out what this W is? Okay, so towards that end, what PCA does is a fine. Suppose I have reduced. Now, how do I go back to X from X reduced? That is, again, if I undo whatever I did, for example, X reduced was N times 1, I multiply with W transpose 1 times P, then if I use a proper W, I should get very close to the initial data. So now what you're trying to do is, you're trying to encode data and you're trying to decode data. Encode into X reduced, decode from X reduced going back, right? So this is a very simple illustration. Now, the way we figure out what this W is, I would like to bring X and X hat close to each other by setting up this loss function. This is X reduced and this is X hat. So if I minimize the mean squared error between these two to figure out what this W is, I get the optimal projection, right? So optimal projection. And this W itself is called as the principal component. Okay, now what this basically W is doing, if you look at what X red is, X had basically features, right? So for all these examples, it has X1, X2, and XP. It has P features, and W is a vector which is of length 1, length P. So X reduce is basically doing X1 W1 plus X2 W2 plus XP WP. So it is trying to combine all these features, linearly combine all these features to get that one dimensional, right? So now this one can be more generally a d-dimensional space, right? So where P is much greater than D. Okay, that is what we would like to do with PCA. Again, an illustration of what PCA is doing is the following. Again, I have data that is distributed along this particular axis. Now, you see that although it requires 2 dimensionals to specify each point, I don't require all those 2 dimensions because I can simply retain whatever information was there in the higher dimension space by reducing the projecting onto a lower dimensional space. Now, there are multiple ways to project, and the 3 example axes is shown here. I can do projection along this particular solid axis, where this is what you get. I can project along the dotted axis C2, where everything is projected between these 2 points, everything is shrink, and some other arbitrary axis where you get this. Now, the question is, what is that axis that I need to preserve or project on? And that is given by solving this loss function, okay? So optimizing this loss function, and W is giving that optimal projection to find the correct axis. And it so happens that if you solve this, you get the right axis that preserves the maximum variability in data, and that is what principal component analysis does. So I have math here. I'll not go through the math, but just put here for the sake of self-containment so that you can go through that at a later point. But as I was telling earlier, all you need to do is use any of your favorite package, and then you basically tell the number of dimensions and the input data. And what you basically get is it is going to compute, say, the do an eigen decomposition and give you the principal components. Okay. So just some illustrations to see what is how powerful is this PCA and what are the what can we potentially do with this PCA is by looking at this again MNIST data. So if you recollect this MNIST data, each image was 28 by 28 pixel, which is 784. Okay, so that's 784 dimension. Now, which means that if I vectorize every image, I have 70,000 examples times 784. This is my X matrix. 70,000 number of digits, 784 is the number of features. Now, using this PCA, if I reduce this to 70,000 times 154, this is what I get, right? So I again reshape it to a certain shape so that, okay, I can make a square matrix out of this 154. This is what I get. So if you see that whatever information was being conveyed in 0 is still preserved, 1 is still there, but I'm throwing away a lot more features, about 80% of the features. Not much information is lost. And that's kind of intuitive from the picture, because if you look at any image, it's mostly background, nothing is changing, and the pixels are kind of very nicely ordered in that pixel. Okay, so that is an illustration of what PCA does. And what you can also basically, but again, you can also use this for visualization. For example, pick 2 components instead of 154, and you see that ideally what you would like to have is like all these numbers are clustered. 0 forms one island, 1 forms one island, 2 forms another island. But you see that if you project it on 2 dimensions, 154 dimensions, you nicely preserve whatever was there, but that is difficult to visualize. But if I do a 2-dimensional plot, then everything appears as one big blob, right? And I cannot do an exploratory data analysis. So that basically leads to development of neural network-based models to do such visualization and dimensional reduction, or extracting those features that are relevant. Okay. So any questions so far about this quick intro to PCA?
Sir, when you were specifying the number in components equal to 154, so how you have decided that like 784 was the original number of components?
Yeah, so that is, yeah, here it is usually through measuring this loss, right? So suppose a similar loss. So if I choose like, say 2,
Yeah.
for example, to get this visualization, then the loss would be very high, right? So for example, if the loss is like, say within 5%,
Yeah.
then that basically means that not much information is lost, right? So between going from this back to the original data, if that loss is minimal,
Yeah.
that means that, okay, if I again use the compressed data to go back to the original image, nothing much is lost. So that trade-off, you would see, like if you plot the loss versus the number of components, you would get something like this, right? So, and in this particular case, you would say 95%, and that happens to be 150. And then if you choose like 2, then it will be like, say 2 would be somewhere here, and that is like 10%, which means that I'll not be able to, if I do PCA with say 2 components and try to plot this picture, that 0 would not look like a 0 anymore.
Okay, so we have to try and see like where the loss is less.
Yes.
No, we need to calculate, like we need to see, right?
Yeah. So it is basically like sweeping from say yeah, something like 2 to 784, right?
Yeah, yeah.
While doing
Okay.
so, you would get this elbow type picture, and
Mhm.
you would basically choose whatever is there. So this
Okay.
is for dimensional reduction, but for
Mhm.
visualization, you would like to always restrict to 2. And because 2D is something that we can easily visualize, but it so turns out that if I use 2 here, then nothing much can be visualized. Ideally, I would like to see these islands, right? So 1 is here, 2 is here, so that I can know that, okay, there are these 10 classes. But if it appears as one big blob, that basically means that, yeah, I'm throwing away too much information, which is not helping me to understand what is going on. I cannot do any analysis with such information.
Okay, sure. Thanks, sir.
Yeah. So any more questions? So I put this note here. So yeah, you can go through this. So the basic idea is that the underlying tool that is used is the eigenvalue decomposition, right? So now this was the basic idea. So behind PCA, you're trying to encode and then decode. Now the question is, can I use a nonlinear way of achieving the same thing? And how should we use neural networks to mimic what PCA is doing? The hope is that I can encode better because I'm using a nonlinear function. And if I'm encoding better, that basically means that the hope is this 154 can be reduced to something else, right? So this 154 is determined based on the operations that we do. Now, if I use something more complicated, the hope is that 154 can become 70, right? So towards that end, autoencoders were proposed as a very powerful tool, and one of the first neural network models towards these generative AIs. So if you look at an autoencoder, it has strong resemblance with PCA. The architecture is, you can use an MLP, a convolution neural network, and RNN, but what is going on is something very interesting. So you have input data, which is, say, X, which is a length P vector, which is having P features. Now, this P feature vector is encoded. So this P becomes some encoding, which is, say, let's call it as H, the latent space. And this is, in this particular case, P is equal to 6. 6 becomes 2. And then we would like to reconstruct back the input data. And this is again of length 6 times 1. Okay. So going from X to W transpose, we got back to the original dimension. But now we are not doing any linear operation, but we have a neural network that mimics what we are trying to do here. So in other words, this H itself is some nonlinear function of my input data. Okay. And then the output X hat is some function. It could be different set of parameters or same set of parameters as the encoded data, right? So you would feed that as an input to go to X hat. Now, the way we figure out this phi, etc., the parameters, which are basically the arrows of this neural network, right? So the arrows have weights associated with it and biases associated with it, that you figure out by minimizing the loss between input and output. And this loss is some function of the parameters of the neural network. Okay. So the idea is, given any input data, I should be able to encode whatever information is there in that data. We call that encoding as a latent space. Using that encoded data, we should be able to reproduce the inputs at the output. Okay. So this is a very powerful tool. Now, if you show me any a sequence of ones, right? Or images of ones or ones and twos. Now, this encoder is basically capturing everything that was relevant for that one with the reduced dimension. And now, if I want to decode, I now have a decoder. So now this is basically your generator that is often used. Now, if I want to generate more such examples, I can use this generator to generate my input looking like data. Okay, so is that basic idea clear? So what we have in between here, the layers that we see here are basically the MLPs. Only thing is that MLP is structured. MLP, it could be RNN, CNN, but it is structured to have this bottleneck. We would like to go from a higher dimensional space, feature space, to a lower dimensional feature space. We want to encode information in fewer features as possible. How do you pick 2 or 3? That is a hyperparameter. But then from that, we should be able to faithfully reconstruct the data. It need not be a lossless encoding. It usually is a lossy encoding, but the loss need not be 0, but it can be something small. Whenever it is small, we can leave with that. And that is what leads to the autoencoding architecture. And now, as we know, say the encoding itself, if I use a single layer MLP, then this is basically some nonlinear function of weights and biases along with the input. But now, if I replace this with, say, the operation that we are using with a linear operation, ignore the nonlinearity, I basically get PCA, right? So that is, in fact, can be verified for the same toy example that I mentioned. So if you look at this image, I can basically set up an encoder decoder, but with a linear layer, right? So sequential layers without any non-linearity. So this is basically a set of linear layers, or even you can use a dense layer to model this. And it so happens that the autoencoder, where it's a combination of an encoder and a decoder, you put those two, encoder and decoder, together and train it using an M. It is basically figuring out what PCA also figured out, right? So whenever linear data happens, I mean, the linear model happens to be the optimal, the nonlinearity basically reduces to a linear model as well, and it is going to figure out what PCA does. But for more complicated tasks, it is going to figure out what this nonlinear transformation should look like, right? So this I already explained. So you have data, you go to the latent space through some encoding function F, and then you decode from the latent space back to the data space, which is your guess about the data, the input data. And as you can see, there are no labels here. I'm simply using the input data. There's nothing like yes or no, spam, ham type of labels. I'm just encoding and decoding with the data. I would like to mimic the input at the output of this neural network. The main catch is, I'm not, so far in all the neural network models, what we were interested was the output layer. The main catch here is, I'm not interested in the output layer, but I'm interested in this intermediate output, which is the encoded data. Okay. And using that encoded data, I should know a decoder. So what that basically means is, I can now generate, if I know this encoded data, I can keep on generating data samples. Okay. So that's the basic idea. And if you're using a linear activation function, basically we have PCA, but if you apply it for data sets where PCA does a good job, you can basically use this autoencoder to also learn what PCA does. Now, since we are using a layer that is a bottleneck in between, what you see here is like you're increasing, reducing, and then increasing, right? So this bottleneck, because of this bottleneck, it is also called as an undercomplete autoencoder. We always want this because you don't want such an architecture, because this is a direct input-output mapping. If I have P2P features, then that doesn't convey, I mean, that is not what we're interested, right? So also you're not interested in something like this, right? You don't want to over complete your data, right? So these are architectures that are not interesting. We are interested in this undercomplete autoencoder. So the main purpose of the autoencoder is basically to summarize, as the name indicates, encode whatever is going on in the data with as few features as possible. So dimensional reduction, visualization, and some more applications that we will see as we progress, or to generate data, right? So that is the main purpose. So if I know the decoding function, starting from that latent space, I can start basically calling this function to generate more data samples, okay? That is the main purpose of autoencoders. And what is of interest is the decoding function, okay? So just like a quick poll. On autoencoders and its relation to PCA. We will see how this deterministic way of autoencoder is generalized to basically generate samples using a variational approach as we progress today. So you will be able to appreciate autoencoders next to the applications that I will showcase through this variational autoencoder. At least I'll introduce that so that we can continue the discussion on that in the next lecture. So let's end this poll now. So it kind of implements the PCA. PCA involves eigen decomposition, which is usually cubic complexity, right? So if you have many features, then eigen decomposition is not the preferred way, but with lower inference time, because if you look at any neural network models, the main advantage is once the model is trained with any deep model is that you are basically implementing a set of matrix vector multiplications, which is the simplest operation that you can think of, right? So in that sense, it has lower inference time. So I'll give some code snippets of different autoencoder architectures that is commonly used as we progress, and later on showcase a couple of applications. So this is again keeping in mind this MNIST data example. So you have 784 units in the input layer, or 784 features because of the 28 by 28 pixels. And this is a deep autoencoder where 784 becomes 100, 100 becomes 30, and this is where we have the encodings. Okay. Now, to decode, I have to go all the way from 30 to 784. So this is the encoding layer, and this is the decoding layer, right? So that's the bottleneck that you see here. And coding in, as in programming in Keras is kind of straightforward, very similar to MLP, except that to segregate the encoder and decoder, you would write it as two sets of sequence layers. So dense input 100, 30, 100, and then reshape it back to 784, right? So that takes 30 as an input. Now you augment these two encoder decoder models and train it together, right? So you would learn all the weights of all these models. And what, as I said, what you're basically interested in is the output at this point, which is kind of summarizing, doing a feature dimensional reduction, or you can use the decoder to basically do many tasks like denoising, imputing, as we will see later on. So one important thing that you need to keep in mind is you need not restrict your layers to a dense layer. You can, for instance, use a convolution layer or an RNN layer, which is fine, right? So it is okay to use any of the layers that we have seen. Selu is a variant of the, I had this list of activation functions. So Selu is a particular variant of a ReLU, which is kind of doing something like this. ReLU, if you remember, 0 in the negative region, and then it has a slope in the positive regime. So now Selu, what it does is it has a parameter to control the slope. Instead of having a slope of 1, you have a parameter to control this. And then it also has a slight exponential decay in the negative axis. So it's a variant of ReLU. It's another activation function. Okay? And in this particular example, there is no reason why to choose ReLU over Selu, right? So just as an illustration is provided here. Okay, so very important about autoencoders. Why should what happens if we have an overcomplete autoencoder, right? So what do you think could happen? Let's discuss that once we answer this poll question.
Professor, just answer one quick question. Whenever we encode some data and then decode it, the input and the input that we gave it for encoding and the final output when we decode it would be same or would be similar?
So that is the discussion that I would like to do, and that's the
Okay,
reason
sure,
behind
sure.
this poll. Yeah.
I'll wait, Professor. Thanks.
Okay, I'll end this poll. Yeah. So far, I have been advocating that we have to use an undercomplete autoencoder with the encoding space or the dimension to be smaller than the input dimensions. Now, imagine, so with that, what is going to happen is that the loss will never be 0, right? So to look at that, let's take a look at this PCA example. So I had X, which is say n times p dimension. Suppose the input, the feature size and the encoding size is the same, which means that W is now a P by P matrix. There's no dimensionality reduction going on. Okay. So now the reconstruction is W, which is again a P matrix. Now, if you try to minimize this loss, what do you think is the optimal W that would get this loss to 0? Any guess? Any W that would
result in
an identity
larger
operator.
than the
Identity.
Yeah, such that WW transpose is identity. Such operations are called as orthogonal transformations or unitary transformations. For example, a rotation or a flip. These are matrices that give you WW transpose is equal to identity. This is going to give you a zero loss. Now, this is the only possibility where I get a zero loss. Now, anything else that I use, right, that would not lead to an identity would give me a loss that is non-zero. So the message is, what we are trying to do is, I don't want to reproduce at the output the exact input, but I would like to stay close to the input. More specifically, I would like to stay close to the distribution of the input, generate similar images as the input. And that is achieved with the undercomplete case. Even if I use an overcomplete case, it is a special case of this identity operation, right? So I can basically throw away this extra dimension and get back to the identity matrix. But if I use something like W, which is P times D, D is smaller than P, the loss will never be zero. That gives me some freedom to move around a bit in the input space to start generating points that look similar to what was there in the input, but not exactly the same. Now, if you look at any loss function of an autoencoder, you would not want to train such that you get a zero. This is never desired. You would like to train it such that you go to an error that is smaller, but not close to zero, right? And by choosing that encoding space to be smaller than the feature dimension, you would maintain this gap, and it is sufficiently generalizing to entire input space, okay? And I hope that answers the question that was being asked. So now, okay, fine, I look at the encoding. What do I make out of it, right? So does it convey the information that was there in the input data? So the previous example was on this MNIST, fashion MNIST. You train this particular network with this particular number of hidden neurons, etc. And then you look at the output at this point, the codings, right? So what we call as codings, and then do a TSNE plot. Okay, TSNE plot is to visualize, and you see that most of the data is basically preserved, right? So whatever was happening in data, you see those islands that we wanted, right? So there are like t-shirts and sandals, etc., that have been categorized. If you see here, the different type of trousers are put together, all the dresses are together. So you see what is going on with the data, which means that the encoding space is actually preserving whatever was going on in the original data. Now, to go back, all I need to do is I need to sample points from one of these encodings, pass it to a decoder. It's going to generate an image that would look very similar to a boot or a t-shirt, right? So since there is some loss going on, so you're going to generate more samples from that distribution and not exactly the same training data, okay? So this is another, the other purpose of putting this code snippet is to also introduce this TSNE, which is a very powerful and important tool that you need to be aware of. If you already know, fine, but if in case you don't know. So TSNE is again a very powerful data visualization tool based on manifold learning. The idea is that, yeah, I mean, you basically give the dimensions. So in this case, it is again doing a 2D plot, give whatever was in the encoding or the output of the any model that you have. If you want to visualize what the features are looking like or what the data is looking like, you give that as an input, give the dimensions, and it is going to give you a 2D picture that you can visualize what is going on with the data. You need not do this for autoencoding per se, but as I said, any input data, you can apply this TSNE plot. Okay, so now this is a very important and an interesting concept. I'm using this to using autoencoders to illustrate this, but this concept can be used for cases where you have a lot of data, but only a part of them is labeled. So suppose, imagine again going back to this MNIST case, I have 70,000 images, right? So we have captured many images of this handwritten digits, which are those 28 by 28 pixels, or these apparel pictures, 28 by 28 again, 70,000 of them. But not all of them are labeled, because labeling is an expensive procedure. I need to have a standard, gold standard to basically design the labeling protocol, right? So there has to be either a human intervention or there should be a protocol. For example, like labeling these 0 to 9 digits is kind of straightforward, right? That you just basically ask all your friends to start labeling 10 per day. You will be able to do that within a month's time. But imagine going through, say, radiology images, right? X-rays, or something more complicated like fault diagnosis in a industrial machine through, say, audio data. That requires domain expertise and it is labor intensive, right? So in that case, you might be able to maybe label, say, 10% of the data or maybe 1% of the data, and this, let's say about 700 of them are labeled. Okay. Now, the question is, I have 70,000 data samples, out of which only 700 are labeled. Now, there are two ways that you can deal with this. Either I use only 700 of them, this using a super learning procedure, doesn't matter, right? You could use logistic regression, MLP, etc., or more complicated models, but the philosophy remains the same, right? So now I can use a supervised learning model to train train on these 700 examples. Now, because I have limited examples, I cannot have a more complicated architecture because I have limited training data. And I cannot basically have an architecture that has a billion parameters, right? I don't have limited samples. The other option is, let's forget about supervision, and then let's only focus on those 70,000 examples and do some unsupervised learning method like PCA, etc., just to visualize. But I don't have a model to do a certain downstream task. So these are the two extreme worlds that we have. Interestingly, with autoencoders, what you can do is you can think of best out of these two worlds, and that is known as unsupervised pre-training. So now what you would do, because you know autoencoders, is the following. You would use all those 70,000 examples, train them in an unsupervised way, and in phase 2, you would change the decoding layer with something that is specific for a task. Say, add one more hidden layer. Okay. So this is my feature latent space, the coding space. I add one more, say, one MLP output layer, say with softmax, and train using those 700 examples that I had labels with. Since now I'm training, and while doing so, I'm freezing the weights of this. Okay, so similar to what we did with pre-training, this is unsupervised pre-training, but the model that I'm going to use for pre-training is the one from autoencoder, not somebody that trained on a different data set, but from the same data set that I have. So I can freeze the parameters and only train this. Now, since I'm only training, say, one layer of MLP, those limited samples that I had, training labeled samples that I have, should suffice. And this process is called as unsupervised pre-training. And this is one important use case of these autoencoders. Okay. So is that clear? Any questions related to this? Okay.
So, Professor,
So
sorry, Professor, in the
yeah.
last slide, so in the output layer, we are using softmax.
Huh. No, I mean that's for this MNIST, right? So I mean you have 10 classes, that's why you use softmax.
Okay. No, but
Yeah,
I mean,
that's just for this example, right? But yeah, I mean, so the same logic can be extended. For example, if you're doing regression, then you would use something more appropriate. But the point is that you only add limited number of layers. Instead of the decoding, you replace the decoding with some decision-making layer.
okay.
Yeah.
Professor, so the purpose is we will be using the small, I mean, the encoded layer only. There is no need for using input and hidden one, right? Hello.
Hello. I'm not able to hear, Professor.
Hi, guys. Professor facing some power cut issue at his place. Just wait for some time. He'll join again. Okay.
Raju will inform on WhatsApp group
Sure, sure.
when we can rejoin.
We can drop off now or
No. Please be here only. Professor will join you.
Okay.
I'll inform in the WhatsApp group for remaining people, those who have dropped from the call.
Can you all hear me?
Yes, Professor.
Yeah, so
But
there
no
was
video.
some page here and everything went blank. Let's see. So you're able to see the screen and then hear me all right, correct?
Yes, with no video.
Okay, video, let's see. Okay, let's see. I mean, let's try to continue with the setup that is working now. Yeah. Okay, so yeah, so this was related to pre-training, unsupervised pre-training. So there was a question before this. What can you repeat? What was the question?
Yeah, question. Professor, my question is like the main advantage of this unsupervised pre-training is the input feature matrix or dimensions will be reduced, right?
So the
For training the model.
yeah,
Yeah.
so the main advantages, so compared to so the setting, right? So we had like 70,000 examples, and out of which only 700 were labeled. Now, the main advantage is like I would like to use the entire data, but still solve a downstream task at hand. Okay, so that is the main advantage. I would like to use all the data samples that I have. And so if I want to use all these 70,000 examples, the only way I can do is some unsupervised training method.
Understood.
Yeah. Now, once I have trained using those 70,000 examples, now what can I do as I still want to use that model that I have already trained, but add something more to specify for my downstream task at hand. Okay. And that is done through this one layer of multi-layer perceptron. Is that okay?
Yes, Professor. Yes.
Professor, here in phase
Yeah.
2, we
So
are sorry.
Yes, please go ahead.
We are using very limited number of samples. Like our input phase 1 has 70,000 samples, and phase 2 we are having 700 samples.
Yeah. So see, I mean, when 70,000 samples, I'm doing auto-encoding. That also I'll try to answer both your question and Gaurav's question together. The main advantage of doing phase 1 and phase 2 as described here and not vice versa or the other way around is that because when I'm training in phase 1, I don't require any labels. Okay, so that is unsupervised training. I can do autoencoder business. Now, phase 2, all I'm training is a limited number of neural network layers. So for example, in this particular case, one MLP with maybe say 10 neurons or 20 neurons. So now to train those 10 neurons or 20 neurons, the limited label data I have would suffice. Now, if I do the other way around, then I would also have to train these and the hidden layer 1 and hidden layer 2. And to do that, I don't have enough data, right? So I have very limited training data. I would require more data to train a larger neural network. So the point is, basically you can extract the features that are task agnostic. So here you're getting something like task agnostic features, and then you're fine-tuning those task agnostic features to a particular task at hand, right? So this feature is universal. It's not limited to that particular task. So when you have more labeled data, fewer unlabeled data, it is okay to ignore the unlabeled data, right? So if there are like 65,000 labeled data and only 5,000 unlabeled data, you can train using those 65,000 using the usual approaches. Now we are looking at a setting where you have very less labeled data compared to the overall data. Okay, I hope that answers all your questions, both Gaurav's and I think I don't know the name, but I hope it answers the question. So, as I was telling, you need not limit yourself to an MLP architecture. You can basically use convolution layers also if you're dealing with not just this fashion type MNIST data in an autoencoder, but a more complicated model, say more complicated data, for example, like a 13 megapixel data, but you would still like to extract the features that is not specific for a particular task, but kind of universal. So in that case, you would simply replace the dense layer with a conv2D and a mix of conv2D and pool layer. But the decoding part, because we are trying to reduce the dimension and then go back to the original page, you recall that convolution operation always reduces the feature map size. That can be achieved through for encoding, but for decoding, you use something known as a conv transpose layer. And what conf transpose layer does something very similar to conf layer, but it increases the dimension. Okay, so increases the dimension of the data again by using a pointwise multiplication and addition. But instead of doing pointwise multiplication and summing, you retain the pointwise multiplications as shown in this example. But the main message is the architecture within the encoding and decoding, you need not limit yourself to MLP alone, but as you would answer in this poll, you can think of multiple architectures. Yes. Yeah, so I could not find the poll question, but anyway, I mean, I already told the answer. So now in the remaining 10 minutes or so, I'll look at different applications of autoencoders. One is the anomaly detection. We'll do that in with two different applications, and the other one is denoising autoencoder. So in denoising autoencoder, as I was initially telling in the beginning, the idea is the following. You have a noisy image because you take pictures that are blurred or pixels are missing. You have a tabular data, you don't have entries in the tabular data, but you still want to do analytics over that, right? So you still want to do data science over that. Now, how do we do that? One way is to use this denoising autoencoder. The goal is the following. You have input data and you train your autoencoder by artificially introducing this noise. So I have data X, I have noise, and what you train your data is through this artificially introduced noisy model. So here the input is X plus N. You train an autoencoder, right? So you train this autoencoder that has this bottleneck layer. Now, what you're trying to actually do is at the output, you're trying to mimic the input, which is the noiseless data. So artificially, you're feeding in the noisy data, but at the output, you want this to be close to X, which is noiseless. Okay, so you want this to be noiseless. Now, how do I do this? Okay, so when you train a denoising autoencoder, the decoder basically is trained to be a denoiser. Similarly, if you have input image, so this is your encoding. So you're artificially dropping off certain pixels. So I have an image, I would drop off certain pixels intentionally in each training example and train the autoencoder with that drop pixel image. And then at the output, I want the output to be close to a complete image. Okay, so now you train this autoencoder, and now at the inference time, what you do is the following. So you've trained this autoencoder to be a denoising autoencoder or a imputing autoencoder, which is also called as a denoising autoencoder. Now, in the inference phase, you get a noisy image. Okay, so now that noisy image is fed here, but what it tries to do is, because it is trained, the decoder is trained to denoise or impute, the noisy image will be denoised at the output. Okay, so that is what you see here. So in this particular case, you get noisy images as input, and the output, you basically have a denoised image, right? So which is either you have image with missing pixels, the input image is filled, right? So it is imputed. So you can do this for images, you can do this for tabular data by initially training your autoencoder with data that mimics the noise that you expect or the missing points that you expect. And the inference phase, you pass that through the encoder. So you have trained all the W's and B's. So it is simply basically doing that input-output map, but the output is going to figure out what the labels are, right? So that is what the denoising autoencoder does. Now, another application of autoencoder is the anomaly detection. Now, anomaly detection, this is like an ECG data set, but you can also think of doing anomaly detection on, say, as I said, like engine noise or any health monitoring tasks, fault diagnosis of your industrial equipment, and so on. So it is done as follows. Now, the autoencoder is trained on nominal data, the normal data. Okay. Now, the goal of an autoencoder, recall, is to reproduce at the output something that is similar to the input. Okay. So now you train your autoencoder on a normal data. Now, during training phase, you would get some training loss. And because you're not able to set that loss to 0 because of the undercomplete nature of the autoencoder, so you would get a training loss, say of, in this particular example, say of yeah, so it's going to decay. So let's say set a threshold of 0.03. Okay, some threshold. Now, you have trained your autoencoder, and now you would deploy that system with a trained autoencoder. Now, what it does basically is you've trained your autoencoder to reproduce data that is nominal. Now, whenever you get a nominal input, x nominal, it's going to give you x hat nominal. Okay, you measure the loss. The loss would be around this region because it is trained on that particular class of data, which is nominal. The moment it sees anything outside that nominal data, for example, it is giving you an anomalous x abnormal, then it is going to reproduce x hat. But in this particular case, the loss would be much higher because it is not the class of examples that it has seen. As a consequence, the error would fall on the other side of the threshold, like what you would see here. Now, you can basically do a simple hypothesis testing by looking at the test loss, whether the test loss is falling on one side of the decision boundary or the other, to basically decide whether there is an anomaly or not. So you can use autoencoders to do anomaly detection, which is a very powerful tool, as we will see in a more practical application. It is actually being used in this Airbus subsystem. All of you might know what this International Space Station is, which is basically recording a lot of telemetry information, among others. And one of the subsystems within this International Space Station is maintained by this Airbus company, which also manufactures all the airplanes. Now, of course, what is important is to do fault diagnosis of these missions, because it's not simply that I take a bus, go to that unit, fix the machine and come back. It's a very expensive endeavor to go replace or to make decisions based on those faulty sensors. Now, traditionally, what was being done is that all the process was manual. So there is like a log that was being dumped, and there is a manual engineer who's manually going through all the data record to see if there is an anomaly or not. Now, instead of that, they use now an automatic way to detect anomalies based on the simple principle that I mentioned previously, where they use an LSTM architecture. It is because it is a time series data recorded for many different telemetry parameters. The numbers are here. So use an LSTM architecture, and then you basically use the idea that I mentioned previously to detect whether there is an anomaly or not in the data sample, right? So this is one realistic use case where autoencoders are used to do anomaly detection. So what we have basically seen is that autoencoder is a powerful tool to do encoding, and not just encoding, but it is also useful for, say, denoising, or it is used for anomaly detection or imputation, right? So there are multiple applications to that. And what is also very important to notice is that the architecture is simply the MLP. The only thing is that you will use a bottleneck layer, but this underlying neural network could be one of the three basic architectures that we have seen so far, right? Either it could be a CNN, MLP, or an RNN, right? In particular, this uses LSTM. Okay, so what I would do is I would just introduce this particular thing in one slide and maybe few seconds to just convey the idea and set up the context for the next lecture, and we'll conclude at this point. So now imagine the following, right? So now, so far, we had this autoencoder, which is going to give you the codings, and that coding is being decoded. So we had X, which is going through some nonlinear function, which is giving you this coding, and then that was going through some, say, decoding layer to give you X hat. This is what we have been doing so far. Okay, so now imagine the following. Suppose I make this random and I simply draw samples from the distribution from which the codings come from. Then basically I get a generative model where I can simply draw samples from that coding space and start generating X hats. So let's focus only on this picture, and we will conclude with the discussion here and go through the details of variational autoencoder in the next lecture. So we have this input space. I have a lot of these, say, MNIST type images, which belong to different classes. Now, so far, what we were doing is we were trying to deterministically model H. So for each example, there is an H encoding, right? So for a certain example one, there is a H1, example two, there is a H2, and so on. I get these encodings. But instead of having the deterministic mapping, if I can get the underlying distribution of H, and if that distribution is tractable, for example, if I model that distribution to be some Gaussian, and with some mean and variance, and figure out what these mean and variances are, now all I need to do is I need to draw samples from this distribution and feed it to my decoder. If I do that, every realization I draw, I get a new realization of X hat. And that is the basic idea behind using autoencoders in this probabilistic or variational setting to generate more samples of data. So you use your training samples, right? So all the input data that you have, not to learn H, which is deterministic, but I learn an H such that I know its distribution. In particular, we limit ourselves to Gaussian distribution and start sampling that Gaussian distribution. And every sample, every random realization that I pick of that Gaussian, I feed it to the decoder. I'm going to generate an X hat, a new X hat, right? That is the remarkable development that led to many generative models. Some of very interesting things that we will see in the next lecture on generative adversarial networks as we progress. But this basic idea, going from autoencoders to have a probabilistic perspective of latent space and start sampling that space to generate more samples that mimic the input data distribution, that is very important, right? That was a very important development in the story of this Gen AI. We'll continue discussion on this variational autoencoder in the next lecture as well, along with the discussion on GAN. So with that note, let me conclude today's lecture, and I'll be happy to take any questions. And I guess there was also a question regarding a mini project, right? I don't know if that person is still around. I can answer that question as well.
Yes, Professor. So regarding this mini project, there was something around time distributed, which was wrapped around convolution networks. This kind of code was there in one of the hints mentioned in the mini project. So related to time distributed only, I wanted to know like how exactly will this kind of work?
So, and the underlying data was
the underlying data was video samples of which we are taking extracting frames, and in a sequence we are trying to the final outcome is to predict whether a person is jogging or running or walking, something like that.
right. Yeah. So now if you maybe I'll create a new slide and explain the yeah. So now, okay, so what you have is like input data, which is a sequence of images, okay, which is kind of time series data, right? So it is time series data, but each time point is not a scalar, but it is an image. Now, what you have to do is the following, right? So, and the output is basically to detect one among the, say, 10 classes, right? So that you mentioned. Okay, that's the basic task. So now what you have to basically do is you have these x zeros to xt, say t frames of images that you have. Now, each frame will go through initially a CNN plus all that pooling, etc., to basically extract the features in an image. Okay. Now, that one goes through an RNN. Okay. Now, this RNN basically has some thing from the past that is HT as well. Okay. And now, after this, you would like to make a decision. That decision is basically your MLP. Okay. Now, this entire set of video frames is corresponding to one particular class, right? Is my understanding correct?
Yes, Professor.
Yeah. So in that entire sequence, okay, the person is jogging, right? Now you have extracted the features from each of this. So what that basically means is that the frame is now being transformed to some x tilde t, which is extracted features. So CNN was a feature extractor. Now you get a sequence of features, which is fed through the RNN, and you get an output. That output you have to use to make a decision. Now, if you look at, recall what I was discussing. So now the output of the RNN YT, you keep on getting for t is equal to 1 to t, correct? So for every time, every image frame, you get an output of an RNN. Now, there are two ways to proceed at this point. One is either you only tap the last output of this RNN, that is at YT, and use an MLP to make a softmax output layer to make a decision, or you can use time distributed here. Okay, so time distributed, that is one way to do this. Now, the other way of proceeding at this point is, if you look at again, so is this clear, the explanation that I'm giving you now?
Yes, Professor.
Yeah,
Professor,
so
here the time distributed means we are using for all the images or for only this, I mean, for all the videos or only for the current video that MLP will be used for all the
yeah,
examples, right?
so imagine that the video is a collection of images. right? So it is at certain frame rate, you have,
Correct.
yeah, right? So now the thing is like all these image frames which belong to one particular video example corresponds to only one class. Okay, so I'm
Correct.
getting output per each time, but this is same as jogging, this is same as jogging, right? But our goal is like all these, this is example 1, this is example 2. But this MLP, the goal of this MLP is to look at these outputs of the RNN and decide one of these. But the thing is, all these T outputs correspond to one particular class. Hence, I will not be using T MLPs, but one MLP in a time distributed layer. Okay, that is one way of doing time distributed. Now, the other approach, which I would recommend for you to try, this is a simple approach, logical to do. Now, the other approach is the following. I have different time frames, say 10 time frames of this person who is jogging, time frame 1, all the way up to time frame T. It's the same image, right? All this person is jogging, which is one video example. Okay, this entire thing is one video. Now, when to compute this X tilde, what I'm using is a CNN to extract features from this image, etc. Now, what you can wonder is, can I use the same CNN for all the timestamps? Which means that this goes through one CNN. Previously in this scenario 1, for each T, I had to use a different CNN. In scenario 2, what I'm suggesting is we can use the same CNN or do a time distributed CNN whose goal is to basically extract features from this. And this is going to give you XT tilde. Does that, are you able to appreciate the two distinctions?
Yes, Professor.
Yeah. So in the first scenario, I have T frames. Now to extract X tilde, for first frame, I use a CNN. Second frame, I use, because I know how to use a CNN, multiple layers of CNN to parse through that image frame. Now the next image you show me, should I use a different CNN or the same CNN? Different meaning it could be the same set of filter numbers, etc., but the weights could be different. The second scenario, you're saying that for all these T frames, let's use the same CNN with the same set of weights. And to enable that, what you require is this time distributed layer.
So Professor, out of these two scenarios, in the second scenario, it is obvious that the number of parameters, because there is parameter sharing, the number of parameters and memory will be lesser. But if rest all of the things are same, then which one is more likely to yield more a better accuracy or something?
That is what I was suggesting. That is an exercise for you to do and let me know the next
Professor,
class.
one more question. For in both the scenarios, for different examples, the weights and anyways the layers will be different. The CNN or MLP, whatever. All the layers weights will be different between examples. But for the same example, in maybe in a,
I mean, see the question is like there's one more new dimension, right? There's time dimension as well. Now the question is, the CNN I did not know from till today's class without this time distributed layer. How should I process this image frames? I have a sequence of image within one example. Previously, I was simply treating every image as a different example. Correct?
Correct, Professor.
Yeah. So now the point is, for one example has T images, and I need to do parameter sharing across time as well. And time distribution, as the name indicates, it is distributing across time.
Correct. So in the scenario, that is for scenario 2 using the same CNN for all the distribution across time. What
Correct.
about in the scenario 1, that MLP distribution, is it between examples or within the same example across images?
Yeah. So
That
the
MLP time distribution.
so the scenario 2 also, the MLP layer you would use time distributed, because the entire example 1 belongs to one class. Although example 1 has multiple images, all these images belong to one class. Hence, you have to distribute that decision-making MLP as well across time within an example.
Okay, so behind the scene while training, like within the example, the weights and biases will be fixed for the each example. When coming
Correct.
to the next example, only those will be updated based on the loss and all, gradient
Correct.
descent and all.
Precisely.
Okay,
Yeah.
okay,
So instead
understood.
of
Yeah,
you
got it.
creating TMLPs and saying that all the weights should be the same, this time distributed wrapper will basically automatically do that for you.
Okay, so this then the mini batch means one example is constitute to one unit, or for example, if we take mini batch of 2, so will the 2 examples will be treated as 2, or each image will be treated as 2, Professor, with respect to this
So mini
scenario
batch
video
in this
process?
video case, you will have like 32 examples. This put together, 32 videos will form one mini batch.
Understood, Professor. Yeah.
Okay. Okay. So are there more questions?
Yeah, one
Professor,
quick add-on question, Professor. So whatever I see in this entire deep learning module, whoever has the higher compute power will be able to get better accuracy. Am I correct, Professor? Because
Yeah,
tuning
apparently,
hyperparameters.
apparently that is true. Yes.
Yeah,
Yeah,
because
for
we are
example,
struggling
like,
getting
yeah,
better accuracy. Yeah.
yeah, I mean, so it is true. Yeah, that's also because, like, okay, if you look at the development in the last couple of years, you cannot think of an individual coming up with a chat GPT, right?
Yes, Professor. Yeah.
You require like huge data centers, yeah, infinite compute and energy resources to get to a better model. And yeah, so yeah, unfortunately
Yeah,
or
like
fortunately,
this image nets and all.
but
Yeah,
yeah, so
maybe.
that is indeed true, right? So yeah.
Professor,
Because
I have
whatever we are doing,
Professor,
maybe is a small squirrel, like small squirrel help for our use case. But at the end, it's big players who will be doing bigger things, I guess.
Uh, uh, yes and no. For instance, like say, I mean, this telemetry data, right? Airbus. They cannot simply ask ChatGPT to solve such problems because ChatGPT might not have seen the data at all.
Yeah, it
Like,
depends on use case.
yeah,
Yes.
it depends on the use case. And some of the things, right? Say, for example, like if you want to deploy something on an edge with your proprietary sensor and a hardware, you still require these tools. Again, like there you cannot use ChatGPT or a computationally intensive thing. So I would say like, okay, I mean, we should embrace the newer development while appreciating these foundations as well. That is what I would suggest. And now
Yes.
again, like say, for example, like that is also not bad because then, okay, we can think of what this pre-training is. That also is a development to leverage what people have done and use that for our benefit.
Yes, understood. Yeah, thank you.
Professor, I have a question. Actually, you just taught this deep autoencoder for unsupervised pre-training. So I was thinking this in the context of customer segmentation for CPG industry. Like if we do a survey, actual survey on 5,000 customer, and we want to segment 5 million customer through the model. So this can be a good use case, right?
Yes. Yeah. So, I mean,
Okay.
again, like, yeah, unsupervised pre-training is precisely for such settings.
Yeah, and generally we used to do this k-means clustering also there. So how it will be, I mean, different in terms of result.
Yeah, in this unsupervised pre-training, you still
Mhm.
have some downstream tasks, right? You're
Mhm.
not, the goal is not simply clustering. You still
Mhm.
want to do kind of segmentation or associate some labels to that.
Yeah, leveling. Yeah.
So yeah, so clustering would basically put yeah, into different segments, and you would not know what segment is what. And now to label each of these segments, you require something like this.
But for the first phase, you mentioned there the unsupervised learning. Here, you mean we are using here the layers, right? Different layers in Keras. We are using the deep learning here, not
Correct.
K-means
Yeah, so
clustering.
K-means, it's more like an algebraic steps that one would do, but that is clustering, right? So if you want to, as I said, like you want to also associate labels to those clusters, you require some kind of a supervised model.
Okay.
Okay, let's two quick questions. I'll take Jayanti.
Yes, Professor. Between LSTM and GRU, in what cases is each of them preferred? I mean, for a video classification task.
So whatever experiments suggest out there, see, it's like RNN were first developed, and then LSTM came, and then GRU. So and GRU were found to perform as well as LSTM.
Okay.
So in that sense, you should not see too much of a performance difference between GRU and an LSTM. And GRU is efficient in terms of memory.
Yeah.
So yeah, there is no A or B. It is like simply you can start with GRU.
And I mean, is it something like if there are like in the mini project which was mentioned, if there are like 6 classes of actions that are being performed, can we use LSTM for 3 of them and GRU for 3 of them? I mean,
No, that you cannot. I mean, it's like classification, right? So
Yeah.
yeah, I mean, it's like saying that, okay, for digit 0, I would use logistic regression, and digit 1, I would use MLP. That
Meaning if I divide it into 2, I mean, firstly, I train the model on only for a part of the data set, which has classification for 3 classes, and then I save the model and retrain it with another. I mean, initially I train it with LSTM and then with GRU. Will it help in any way, or?
No, I think, I mean, I would simply use one model.
Okay.
Yeah. Okay.
Okay. Thank you.
Yeah. So AR and ARIMA model, I think Shashi Jain will cover those as a part of business analytics. And I guess with a bit of financial application as well. Yeah, Abhishek.
Yeah, Professor. Regarding these two scenarios that we see in the slide, so the first one, let's say in an example, we have 10 images, 1 to capital T, let's say it's 10. So what is happening? So we have, in the next layer, if we have, say, 4 filters, so all I mean, all these images will go through a subset of these filters, and whereas in scenario 2 all these images will go through all of these 4 filters. How's this? Hello?
Say that again.
Yeah, so in these two scenarios, the input, let's say xt, there are 10 images in one example. In the next layer, if we have, say, the CNN layer, we have, say, 4 filters. So what, I mean, how is this different in these two scenarios? What will be the difference?
so the scenarios, the number of parameters in the first scenario would be more, right? So apart from that, the accuracy or the interpretation of the filters, that you have to basically try and then see. Just by looking at the two scenarios at this level, we can only comment on the number of parameters. And first scenario would incur more parameters, hence more training time.
Yeah. So, I mean, in the second scenario, is it that all these images are going through all these filters, whereas which is not the case in the first scenario?
No, second scenario, it is going through the one filter because
Only
we have
one
this
filter.
time
Okay.
distributed layer, right?
Okay. It's one filter.
Hmm.
Okay. Okay. Thank you.
Okay. Okay.
But the
Okay,
parameter
so-
for the second one is little higher, na, Professor?
Yeah, parameter for this first one is higher.
First one, yes, sir.
Okay.
Yeah, thank you.
Okay, so let's conclude this meeting now. Resume back next week. Thank you all.
Thank you.
Thank you, Professor.
Thanks, Professor.
Thank you.